Looks like we are live and in action. Okey-dokey. Just making sure everything's okay. Just gonna check the stream. Okay, streaming's good. Okay. Hello to anyone joining us online. I'll have this chat open throughout the duration if you want to ask any questions, if you are joining us online. I'm just going to quickly pop outside to test the audio. From what I'm hearing, we should be good. Okay, that's good to me. So I think we will get started then. Hope everyone's pumped for some more 3411 revision. So today I will be taking the first topic. We'll be looking at information theory, which is, I guess, one of my other favorites. I took compression coding yesterday, sorry, and that was also one I particularly liked. And then Matthew will then after that take you through the rest of the topics, which include number theory and some algebraic coding and cryptography, which are all lovely, and he'll walk you through that very nicely. Expect when he shows up here. So attendance form is on the relevant to attending. I'll just show you the slide. If you want to become a peer mentor or interested, please feel free to apply for that so you can help out the first years developing your mentoring skills next year. QR code will be there and recording. Likewise, it is frozen. Yep, so just unfrozen it in person. That will be in the recording. And likewise, the feedback form, if you want to give feedback for how MathSoc is going to run their revision seminars next year, which will, as usual, be a pivotal part of what MathSoc does from year to year. We'll try to improve on them next year. So please leave us feedback for that if you would like to. Okay, so we will start with information theory, which I'll walk through. So the most intuitive link you can make to information theory is in terms of how surprised you are when you receive a certain message. So that's the link we're going to be making between what we're going to call this information and what we talk about with the probabilities of sending a message. The example you can have is that if you have a source alphabet of just two source symbols and one is extremely likely to be received and one is very unlikely, then you would get quite a large amount of information if you were to receive S2, because it only has the 0.01 probability, whereas for S1, since that's very likely, you're not going to really receive much information. You're not going to be surprised by it at all if you do, in fact, end up getting that encoded. So that's what we're going to be talking about, what type of information on average, which we'll call the entropy, in terms of the messages we send. So first of all, we can define mathematically what we say is the information. So this information function also shows up, actually maybe I'll make the link when we get up to entropy, but this information function is quite nice. It shows up in a lot of different places. What we define it as here is for a specific radix r, we say it's the log base r of the probability, and we put a negative here. You may not remember why we put the negative. The reason why essentially is to make this whole expression positive, because if you remember, our probabilities by nature are between 0 and 1, meaning that the information will always be strictly positive. Also, non-negative. It can be 0 if, say, the probability is 1, which is saying if the probability is 1, then you're not going to get any information, because that event is always going to happen, so you're not going to ever be surprised at all. So I believe in the lectures, Thomas went through this slide in the reverse direction, as in he said, these are the properties we want our information concept, our expression of it to satisfy, and then he said that this is, by a specific theorem, the only real function that can do so, up to a scale factor, but you can just take his word that given this is enough to just look at the fact that this information function satisfies these certain properties. The important to, that if you have independent events, when you multiply the probabilities together, you get the probability of that event occurring. And it's also nice from log laws that means that the information you get from that is the sum of the informations you get from each of the events. So the information is additive. You have, I guess you can think of intuitively, the additional information from the events. Finally, the information function is continuous, which is quite nice for us, meaning we can work with it in terms of calculus. We'll talk about how with, say, binary symmetric channels and trying to maximize the mutual information. That's a nice property we'll have in terms of being able to use techniques to maximize and minimize. Okay, so in terms of now the entropy, we will be talking about what is going to be the expected value of our information. So since we can talk about here for a specific event with probability P, if we're looking at, if we're looking about at the all the different events that occur, so all the probabilities add up to 1, for instance, say all the different source symbols we can get with respective probabilities adding up to 1, then what we can get here is that the entropy will be the expected value of the information for each of those respective source symbols that we get. Okay, so we're saying the entropy is a little hard to interpret, I suppose, but entropy is going to be the expected value of the information that we get. So it's a little lower value, lower bound. We'll see in a second on how much information we can carry in terms of our transmission. We'll talk about in terms of the link between the average code word length and the entropy in a second. First of all, you can do some computations just to remind yourself. So this will be actually motivating what we'll talk about. We can, if we want to, apply our Huffman algorithm again on these probabilities. We remember how to do that from yesterday. If you're not quite sure, you can try to rewatch that recording. But then we can also try to find the entropy. So this entropy would be, actually what we denote as H, is H of, H of this set of source symbols would be 0.6 times log base. And what base do we want to use? Binary, so base 2, 0.5 minus 0.6, 0.2 times log base 2, 0.2, and minus dot dot dot. You can see the pattern developing. So if we plug that in, we continue doing that, and we would get the value of 1.57. And if you were to apply the Huffman algorithm, you would, for this specific set of source symbols, you would find that the average length of that Huffman code would be 1.6. So comparing that here tells us that the entropy is, in this case, less than the average code word length. And so we will talk about this formally, about how the entropy forms a lower bound of what our average code word length can be. So we can think of the average code word length as the, I guess, the amount of information we can pack per source symbol. So we're saying we can't do more than what the entropy, the amount of, I guess, information on average there is, based strictly on the source symbols. We can't do better than that. It's like a threshold lower bound that we cannot exceed. Just a little note I forgot about in terms of the entropy, just in general, why it's important. This does show up, of course, in this type of computer science coding context in terms of the probabilities that certain events will occur. It can also show up in, say, physics, that Matthew would be very pleased that I mentioned, because up to a scale factor, the concept of, not information, but entropy in physics has this exact same formula. But I believe there's a constant in front of it. You may use a different base, but that just means a scale factor difference. Okay, so now what we want to get to, the link I promised will come up in a few slides, but first of all, there's some theorems that you might want to know. The proofs are in the slides if you want to have a look. They aren't too difficult to have a look at. The first theorem that we want to know is the maximum entropy theorem. So what this says is that for a set of source symbols, the maximum amount of expected information we can get is when all the source symbols are equally likely. Okay, so when Q, which in this case would be, Q would be 1 over n, where there are n source symbols, so q source symbols, I see the q source symbols, the probabilities, pi's, are all 1 over q. So we're saying that entropy is the sum of negative 1 over q log 1 over q. And this is a constant factor, so you can scale that out. So it's negative log 1 over q times 1 over q. This expression here turns out to just be 1, and then you can use log laws to write this one as log q. Okay, so on the intuitive level, what this is saying is that we can have a better expected amount of information per source symbol when we are having more closer to uniformly distributed source symbols. So that's the intuitive idea. That there's probably more important to remember that when you get closer to less uneven distributions of the probabilities of your source symbols, then you get more information on average, is what you're saying. Because it just really pops out mathematically that when you have more of an imbalance, then there are cases where you get high information unexpectedly a few times, but on the average you don't get much information. Similar to the example here, where you get a lot of information very rarely, but on the average you don't get much information, whereas when they're closer to each other you get more information. Okay, and that's something that I believe on the intuitive level helped me when I did my exam. There was a question similar to that say wasn't too close to anything that I've seen before in the practice exams. And so just understanding that intuitively would be helpful. If I remember correctly, this next theorem is what is used to prove that maximal entropy theorem. It's called Gibbs inequality, which, if I remember correctly, is proved from using Taylor series, little expansion of the ln. But what it's essentially saying is that if we look at our entropy function and replace the probabilities in the logarithms with another distribution of probabilities, q1 through to qn, then the entropy would be strictly larger. So if you mix up the probabilities, then in your entropy calculation for whatever reason, and whatever reason may be here, for instance, when you want to make comparisons like so, then you have you can't get any smaller amount of information from that in terms of entropy from that in terms of just plugging in the numbers to the expression. But of course you keep the p's here. Right, so this is the theorem I was going to be talking about, the important one that we want to know in terms of comparing the entropy and our average code word length. So here, as I said, the entropy forms a lower bound on what our average code word length can be. So this is called the first source coding theorem. And again, it has a decently nice proof, I believe, similarly using Gibbs inequality. So what it's talking about, as I said, you have your standard setup of source symbols, probabilities, and your then for what it's saying, for any set of lengths, this inequality holds where you can't get a lower average code word length. In particular, the Huffman code word length would be no lower than the entropy, because remember the Huffman code word length is going to be the lowest that you can get. And specifically, though, you can, in this case, if it is nice enough such that all your probabilities are to the negative Li, and you have this k value corresponding to that being equal to 1, then if you play around with the mathematics, again, the proofs are in the slides regarding, say, Gibbs inequality, then it pops out, then you can get exactly that Huffman for that set of probabilities, the Huffman code word length is going to, average code word length is going to be equal to the entropy in that case, if these two conditions are met. So in terms of the proof, again, that's in the slides if you want to look at it. Okay, so what this motivates is that we get closer, sufficiently close really, when our lengths correspond like this to the probabilities. I guess you can maybe ask, if we want this to occur, why can't we just make that? Like, can't we just define the lengths in terms of this? Well, the problem with that is, of course, if you rearrange for the length in this way, you would try to get Li is equal to negative log pi of base r. But the problem is you want your length of your code to be an integer, and this expression might not be an integer. So the best you can really do is try to cop with doing a little bit worse than that, and a little bit worse in the sense that if this is the best we can do, we can't really exceed this, then we just cop off and go a bit above that in terms of just rounding up to the nearest integer. We can't really round down because, again, we can't go better than this. So we say we're content with rounding up, and that's what we call the Shannon-Fano coding method. So again, we have our source and probabilities. What we say is we're going to use the length to be the ceiling, the rounding up of this expression. So if this turns out to already be an integer, and in terms of if this is already satisfied, if this condition is already satisfied, then the Shannon-Fano coding will give exactly, well, the Huffman code and also the code that is exactly that has the average code word length equal to the entropy, which is quite nice. But in a more general sense, we'll look at an inequality that tells us how good it is, but it turns out to be decently good as well. But the Huffman algorithm, by definition, since we talked about Huffman being the minimal average code word length, is always going to be no worse than the Shannon-Fano. But I suppose the Shannon-Fano, in terms of complexity of computing, is much simpler because you just do this. If you're familiar with complexity theory, is just a constant time calculation, whereas applying the Huffman algorithm requires some more linear time. I think n log n, if you're familiar with that, time to calculate the Huffman tree. You can think of, you need to play around with a lot of that. So that might be more expensive, where this one is just a bit more efficient for your purposes, perhaps. Okay, so we'll look at an example of our Shannon-Fano coding method right now. So we're looking at ternary, so r is equal to 3. We have, again, the similar setup of our probabilities. So what we can do, I'm sure you're all confident with these types of calculations, we can calculate what we want the lengths to be. For instance, we want L1 to be the ceiling of negative log base 3 r is equal to 4. And what we have here is that L1 would be equal to 1 in terms of rounding them up. L2 and L3 would be the same because they have the same probability. And likewise, L4 and L5 would be 3. So what we have here is we have the lengths that we want, and we can construct such a code by looking at trying to do so from a tree. We can say 0 here for C1 because we want length 1. Then we want length 2. We can go 1, 0, 2, 1, 3, and 2, because we're working with ternary. We can make 3 branches. We could go C4, and then, oh no, we want the next one to be length 3, length 2, and 2, C4, go 2 here, and since we want the last one to also be of length 3, we can go 0, 0, and go to C5. So a little bit of an inefficient tree because we have open branches here. We could effectively just cut this part off if we wanted to make it a bit more efficient. But we'll say, in this case, Shannon-Fano, we'll just cover it with this function.
There was also a nice thing to figure out eventually. You can find the smallest bound such that 3 to the power of L is less than equal to 1 So for example, in 6.1, like minus log 3, 0.1 is same as log 3, 1, 0.1, which is log 3, 10.
Right, yeah.
So you want to find the smallest 3 to the power of, like 3 squared is 9, which is not bigger than 10.
I suppose, yeah, that's how they teach doing logarithms in year 10 before they have, just
3 cubed is big enough to be bigger than 10.
Yeah, okay. Yeah, so what the gentleman here at Turning Live said is that instead of just computing it using your log, if you want to try to do it in your head, what you can say is, since you have the equation, if you rearrange the equation, basically you're trying to find the L such that 2 to the power of Li.
That's 3%.
Sorry, 3, yeah, sorry, R to the power of Li.
Yeah.
Would be negative Li? Yeah, negative Li.
Okay. Because the negative comes into the 1 on the probability.
Oh, that's right, yes. Yeah, is equal to, greater than equals this. Yeah, so if you find, so if you, for instance, if you're able to compute this nicely, so for instance, if you're looking at 0.1, 1 over 0.1 is equal to 10. So you want to find, r to the power of 1 is equal to, in this case, 3. R to the power of 2 is equal to 9. R to the power of 3 is 27, which is greater than 10. So that's why in this case we used greater than equal to. So let's say greater than equal to. Yeah, that's very cool. Yeah, so that's another way of doing it. Excellent. See, there is just a bit of activity on the chat. Someone's asking where can we access the actual textbook. I'm not quite sure what that means. I'm not sure if they're referring to the slides. Alright, so let's move on. So as promised, we can find, and the code words are here. We'll verify. Yes. Oh man, did I do something wrong with the tree? Let's go in here. 1, 1, 2. That's good. Oh, and I see, yeah. We'd actually, I suppose, alternatively, you can just make the fifth code word from here, and you don't even need this branch, but again, still inefficient in the same way. I guess that's a more conventional way of doing it. You go fill up as many branches as possible, as soon as possible. So the 0 and then 1 for C5 it would be the more conventional way to do it. So yeah, we see there's a little bit of inefficiency with this Shannon-Fano coding method, but what we can say is that we can find an upper bound and lower bound for what the Shannon-Fano average code word length would be. So we know, of course, by theorem we saw before, that it's no less than the entropy, but we can also say it's no greater than 1 plus the entropy. And the reason why we can say that effectively is because when we round up, we're no more than 1 away from the nearest integer, and how that shows up in terms of relevance is because we know we're trying to replicate this type of setup, and so we're no more than like 1 away from that in terms of every L effectively. And this gives exactly the entropy so that we know we're going to be no more than 1 away. I believe there is actually proofs on this slide for it. Again, you can see it in the lectures, but yeah, you can see that 1 plus there comes up mathematically, and that turns out to be a sum over the probability, so you get a 1 plus there exactly. Okay, cool. Alright, I think that's pretty good. Yeah. Okay, so let's have a look at this now. So what this is talking about is similar to what we spoke about before. Well, expanding upon that idea of entropy of extensions. We looked at how when we made the Huffman code for the extensions, for instance, we looked at, say, S squared, where if S was AB, we looked at S was AA, so we're trying to encode more at once, so we could try to get a lower average code word length out of this. And the nice theorem here is that when we make the extension, then what turns out to happen is that for that extension code, our entropy is going to be n times the original entropy, which hopefully makes sense in terms of it makes sense if you think about logs, because you can kind of cheekily say, oh, the n would just go out, log floors. But yeah, the proof is a bit more technical than that, but that's the essential idea. And you can use this to motivate what we're going to say next, which is quite a nice theorem, that if you rearrange this equation based off the inequality we saw before, in terms of using the Shannon-Fano code with this entropy of extension for a particular set of source symbols, then you can see that with this expression, which we saw yesterday as the average code word length per original source symbol, that is going to be bounded below and bounded above, and we can see that this 1 over n, if we take the limit as n approaches infinity, is going to go to 0, and by the sandwich theorem, if you're familiar with that from Math 1a, it's going to say that L over n is going to be in the limit exactly equal to the entropy. So as we take the limit, we're going to approach that lower bound that we spoke about before, which is quite nice to talk about. So the importance of this is saying that, again, the entropy is our lower bound, and it's saying that effectively as well, when we do that technique of trying to encode more and more at once through using our entropy of extensions, trying to like combine words together, then if we do that enough times, then we absorb all the information, which hopefully makes intuitive sense as to why. That means that eventually we get arbitrarily close to the entropy itself. Okay, cool. Alright, so looking back at Markov chains again, we looked at this in the previous chapter. We can also talk about this in terms of entropy and information. So again, we have our matrix and our equilibrium vector. Remember, the equilibrium was the long-run probabilities. It's the eigenvector, whereas the matrix has the ith column being the conditional probabilities of previously receiving the ith source symbol. So what we can define, similarly, how do we define entropy? We can define the conditional entropy based off getting source symbol I, given that we received previously source symbol J. And likewise, we can take the conditional entropy for that, being the expected value of the information of receiving SI, given previously we received SJ. So what that is going to say is, in this case, the only real difference is that we use this conditional probabilities here, which makes sense because we're using that transition in our Markov chain. So it turns out to look mathematically like this, very similar to what we seen before for the entropy. We're just replacing now the ij. We are fixing j here because we have fixed our previous character. Okay, and that corresponds to the jth column of our matrix. Okay, we're summing up over the jth column of our matrix. And what we are looking at here now, in terms of, we can do this very well and fine for any specific different column, the jth column, but we want to look at a bit more overall. So similarly how we took from the information, we got the entropy from the expected information. Now we're going to say the Markov entropy is going to be the expected conditional entropy. So it looks like this. In other words, well, there is probably not too much worth in writing out, but if you combine this in terms of the expression we saw before, it's going to look like sum over j to q of pj times pi given j, h, we should say actually not h, but I should bring this open. It's going to be the sum of the i's on the inside, sum over I of log, there'll be a negative here, so we're just being negative, pij. Okay, and what we can identify this as, if you remember your conditional probability, this is the same as probability of getting j times the probability that we get I given j. So that's going to be the probability of getting I and j. I and j, if I remember my probability. So there was that little revision slide at the beginning of the first chapter in terms of revising probability theorems like that. This is similar to what effectively comes from Bayes' rule. We can also define, though, the equilibrium entropy, which we get similar to how we applied the Huffman code, for instance, on just the equilibrium probabilities. We can get the, for that, those equilibrium probabilities, we can also get the equilibrium entropy. Okay. Okay. So for this example, suppose we have this be our equilibrium probabilities. Just don't worry that it's not really correct. For this example, for simplicity, we're going to say that's correct for the niceness of the probabilities we want to work with. So we want to find HM and we also want to find HE. So HE would be easy. HE would be, say, just summing up all of these. So it would be negative 0.53 log base. In this case, we may meant to assume bits, yes. So 2, is that what you're going to say? Yeah. So bits means 2. So bits would be, bits like pi is in 2, so we'd be looking at radix 2, 0.53 minus 0.15 log 0.15 again, and then plus dot. Well, see the pattern, plus in this one, that's fine. And we can also look at our Markov entropy, which would be, well, it's going to be a lot of terms actually, so we can sum it all up. You'd be saying, let's just express it in terms of the conditional one. So we say it is going to be, what we say, 0.53 times the H What is expect the conditional one? So
Like let's do this one.
HS given, yeah. That's right. HS, thank you, given S1 minus. Okay, so let's just make sure that's all correct. Right, and yeah, you can compute each of these by looking at every single column. It's nicely color-coded for use. You can see the vision of what we're trying to do there. Again, we use base 2. Seems all good. So let's see what pops out in this calculation when we add it all up. So as we said, we're going to compute this, and this, the weighted average of all the conditional entropies, and then we can also get the equilibrium entropy like so. And what we see here is that the entropy is going to be lower for the Markov compared to the equilibrium, which is going to be consistent with what we saw yesterday, because we said that when you use the Markov average code word length, the approximation of that, we saw that that had a lower average code word length than the equilibrium entropy in terms of that specific example list, which is consistent here because we see for this example as well, we have a lower bound for the Markov entropy compared to the equilibrium one. So we can get a lower, in terms of like applying, say, what we talked about here for, say, extensions, similar idea, we can get in the long run in theory, can get a lower average code word length when we apply this more clever Markov entropy compared to just doing the kind of naive attempt in applying the equilibrium. I believe there's a theorem on that coming up. Okay, yep. So here it's an actual theorem that tells us that every single time we will always have that the Markov entropy will be lower than the equilibrium entropy, which is quite nice. And also a quite nice result is that equality only holds when each source symbol are independent of each other. Okay, which makes sense because then you would have there's not much change between the Markov compared to the equilibrium, really the same in the intuitive level. Okay, so you can get in this case these types of ghastly looking summation expressions where we can apply that same idea of Markov extensions. So similar to what we saw before, we are going to be extending to get all the different q to the n, because there's going to be, we're looking at n different symbols, and there are q choices for the first one, q choices for the second one, q choices for the third one, so there'd be q to the n total choices. So what we can look at again is the Markov entropy for that. We'll also have, these will be looking at the conditional, we can compute the conditional probabilities, which is, I guess, a bit tedious, but you can, of course, do it. You can also get the equilibrium probabilities. So this is where maybe if you see something like this in the test, you might want to refer back to, say, Bayes' rule from one of the first couple of slides in yesterday's recording. But in terms of just knowing the probabilities, you would say it's like we spoke about before, say like we talked about probability of I and j. The same thing is occurring here, where we're talking about getting the probability of both these two together in terms of consecutively. Then we have the conditional probabilities on that previous source symbol. Okay. Right. So the last, this is denoting like the last source symbol within this. You can think of this as like a word. The last source symbol in that word would be SJN, because that's what the next is going to be dependent, as in it doesn't really matter too much about what the starting source symbols are in sigma j, just the last one, because that's what's going to be important in the transition. Yeah. So if you're a bit unsure about that, I'm sure there's examples in the slides more going through computations of that. You should have seen it maybe in your test, but we don't have too much time to go into that a bit more. This theorem isn't too important in terms of this part. That's just something you can kind of take the word for it. The kind of n-1 is a little bit counterintuitive, but it does make a bit of sense in terms of, I guess, in total, this would add up to n. So it's similar to what we saw before, but slightly different. In terms of just the Markov one, it would just be n times as we saw before, but for the equilibrium, it's a little bit different because you do have to bring the Markov entropies into it. But what we observe here again is by a similar logic, the equilibrium, if we just apply the equilibrium naively, then it's going to, in the long run, reach the Markov for the original source. So that's saying that this is essentially doing this process of using extensions for the equilibrium is essentially doing what the Markov was not doing originally in terms of using the conditional probabilities, in terms of looking at source symbols as a pack instead of individually. So we get that type of improvement in the long run when using extensions on our equilibrium probabilities. Okay. All right. So sounds good. Now, the last thing I believe in this section is going to be talking about concepts such as the mutual information that we'll get to in terms of noisy channels. So, do you have a question?
Yeah, if there's no conditional probabilities in the equilibrium, like where does the extra information come from?
What do you mean by that, sorry? If there's no condition, so the question was if all the probabilities are independent.
Are these independent or are they just any?
In this case, it's the Markov setup, but they may not be independent.
Yeah, so with the HE, that doesn't encode any like conditional probabilities. Like that's why I'm thinking of this too.
This one?
Yeah, so we should put the HM would have more information that has exponential probabilities.
So you're saying that in the long run, you may expect perhaps that this would still maybe be greater than this one? Okay, yeah. So that's a fair question to ponder.
Isn't that true from a sandwich though?
Yeah, I believe it's proved from what these would be enough to prove it if I'm correct.
Prove it just from using identity 1 and identity 2. So if you have no problem with identity 1 or identity 2, then you shouldn't have problems with identity 3 because you just want to use sandwiching.
Yeah, because we have that previous theorem from before, don't we? This one, yeah, you can start off from this one as a lower bound. This can form the upper bound. I believe that should be really all we need. It's an interesting question. It's just something interesting to think about. But in the interest of time, I'm going to move on for now. So in this case, we will have a set of sources and we'll have a set of sinks in terms of our channel. So we're trying to send from our source to our sink. So these are the possible set of symbols we can send. These are the possible ones we can receive. So we can imagine the A's on one side, the B's on the other. So say like A1's here, A2's here. And I believe usually only look at the case where there's one on either side, B1's here, B2. And there's particular probabilities that we can receive each of these. As I said, this is B1 probability, this is P2. You'll see like the precise notation of what we should use, but you have these probabilities of transitions of getting particular outputs depending on an input. The reason why we have to look at this is because even though like in theory you would want, say, if you plug in A1 as your source symbol or say A2, you would want the respective corresponding code words, say B1 is the corresponding code word to A1, but because of what we may have, which is noise, which might corrupt the signal we're trying to send, there would be cases where if we try to send A1 to get B1 out, we would instead get perhaps B2, which is what could happen. And that's what we're going to be studying here. P3. And yeah, you are given the probabilities of such events. So what we're going to be looking at again, using the entropy now, we have first of all, the source entropy, the HA, which is the entropy calculated using just the source probabilities, which we spoke about on the previous slide. And you can also have the output entropy, which is the entropy calculated using the sink probabilities. And you can use these formulas here for now the conditional entropies. So these are different to HA and HB. This would be effectively how much expected information we get knowing that we sent AJ. And this would be the expected information we get knowing that we sent BI. So again, we can take the expected value of the conditional entropies, as we have done before, to get, say, what we call the noise entropy on the side where we're looking at B, given that we know what A is. So this is the expected amount of information that we get, expected information that we have, given that we know what A is. And likewise, this is the expected amount of information we get, given we know what, expected entropy that we have, given that we know what we received. Okay? And we can also refer to the joint entropy, which so you can say joins them together. We're looking at a diagram for this later on. Is the entropies looking at getting both at the same time, like your ANDs combination. So move on a little bit for now. We'll come back to try and talk about the intuition in a second. So the intuition actually I have here. So the noise entropy is a measure of how much information we get in the output, given that we know what's in the input, as I spoke about, because it's conditional on, say, knowing A. You can look at this as, say, a Venn diagram that we'll look at in a couple slides. And the joint entropy is also understood, in a different way, understood as the information of the channel as a whole, counting for every thing in total. So I know that intuitively it can be a bit hard to remember these sometimes and interpret them, but the more you play into these types of intuitions here, the easier it would get. You can also have these types of propositions where you could say the joint entropy would be, say, the entropy of the set of sinks plus the conditional entropy of A, giving you know what the sinks are. Okay? Which is quite nice, and likewise it's symmetrical for A as well, and also like symmetrical if you flip around, because there's really no difference between A and B here besides this, but you can try to flip that around as well. Bayes' rule would help you with that, and they would be the same this way. There's the symmetry here, which is nice in terms of A and B. Okay, so this is the diagram that I was trying to speak about in terms of what we want. So you can think about this is a Venn diagram. Essentially, we have A and B. You're saying this expression, which is going to be the mutual information, is going to be effectively like the overlap between the two. So the shared information between our sources and the sink, which we're trying to, in a couple of slides, maximize, because it's effectively saying how much information we can actually transmit effectively. What HA is going to be this whole part here. HB likewise is going to be everything in this part of the Venn diagram. And then, for instance, what we could have in terms of the conditional entropies, HA given B, is the amount of excess information there is in A, given that we've already removed what we already know in B over here. And likewise, you can have the same type of symmetric argument. I run out of colors already. I think I have, you can talk about the same symmetric argument in B, given that you already know what A is, okay? Alright, so we're going to look at just some examples now, and that should wrap up this section. Just note that this function that I believe Thomas usually gives you in your test, or tells you can define, is going to be quite useful in terms of using the chain rule to maximize the mutual information later on. So just be noteful that we use this in terms of if you have the binary case, then if you know the probability of one source symbol, that would be probability P. You would say this is one term of the entropy, and the other term would be 1 minus P, because that's the probability of the other symbol. So this would be your total entropy of, say, A, if A had probability P for the first symbol, and then would have to have 1 minus P for the second. What we want to look at here, as we spoke about, A has A1, A2, B has B1, B2, so A here. And what we have is probability of A1 is going to be X, is X. This would be 1 minus X by the symmetry for probably A2. There's only two possible cases. So we could say immediately HA would be H of X given this function. I believe that will be useful later on. And what we're looking at is a transition. We're saying that given we have A1, we have 4 over 5 chance of getting B1. So that would be this transition here, 4 over 5, which would mean we have 1 over 5 chance of getting B1, B2. Oh no, it would be the other way. Yeah. 4 over 5. So this is effectively saying 4 over 5 times effectively we transmit what we wanted to transmit. It's like what's here. Getting B2, if we had A1, is what we want, 4 over 5 times. So what we want to compute is H of A. Looks like I've already done that, unless I made a little mistake. Then we want to compute HB here. So we can use one of the formulas on the previous slide and try to interpret this using that Venn diagram, for instance. So what should we use here? We can use a few different things. We could say, I think we can actually maybe straight away just compute it because we have these conditional entropies and we do have actually we have the entropy for A. So we can compute this as HB given A. Given A should be X times HB given A1. And for computing this, we would use the transitions of 1/5 and 4/5, and then this would be 1 minus X HB given A2. Don't see any problems so far. Let's just make sure that is correct. So H of A would be H of X as we defined by this function. Excellent. And for this, if I made a mistake, no, not yet. Good. So HB would be, as I said, probability of getting A1, which is X, times H of 4/3. Yeah, so I left out, I guess, that detail. This would be probability of getting the entropy of B getting given A1 would be H4/5 because one probability is 1/5, the other one is 4/5. So you can, let's say, P be 4/5. Like equivocally, you can say, like it is a property that H of, in terms of this function, if I can zoom out, yep, let me zoom out, good. H of P equals H1 minus P. So equivocally, we could have said here, say H of 1/5 should be fine. But yeah, you can round that off if you want to see it. It's like that. And likewise, we'd use H4/5 or H1/5 here. So that's fine so far. So the next thing we want to do is to find H of B and the mutual information. Okay, so we know already H of A and we know H of B given A. So what we want in our diagram is this whole part here, H of B. We know H of A. So we know H of A. This is A here, and we know H of B given A, so we know this part. So what's left for us to compute, no, is it? Yeah, what's left for us to compute is, I guess we want to find in some sort of way, well, we effectively want to find eventually this middle part, and I guess that would help us with computing H of B anyway. Suppose we want to flip around the channel in some sort of way. So what we will try to do is we can use one of the formulas where we have seen before. H of B would be equal to, I guess we could find the mutual, the joint entropy. Don't think that would be too helpful here. Maybe let's say it would be, actually, yeah, we can't really find the mutual information. That's more something we
B given A.
B given A? Yeah, that's what I was maybe going to say. B given A, which would be... Oh, we found B given A, didn't we, before? We could find A given B. Yeah, find A given B. Makes sense. Yeah, so we have B given A, and we have A, so let's say it's the entropy of A minus entropy of A given B, so that would be just this overlap, wouldn't it? I'm looking at, will this just be the mutual information? Unless I'm mistaken. But in terms of computing A given B, wouldn't be too hard.
Yeah, like probably mutual information instead of H of B.
Yeah, that's right, yeah. I was going to add another term, but this should be here, the mutual information. The only difficulty would be finding what we would want to do here. We'd have to flip around the probabilities. So we would want to find, I suppose, the probability of getting B2 and probability of getting B1, which would be, say, probability of B1 would be equal to, some different color maybe. Probability of B1 is 1/5, 1 minus X plus X times 1/5 top of X times 4/5. Okay, and likewise you can find probability B2. Wait, isn't it? What I want is H of, oh yeah, wait, no, tripping, yeah, H of B you could just like compute manually. You could just say it's, I guess you don't really need to do this, yeah, I'm complicated. You could just find H of B by finding the probability of getting the first source symbol in B and second source symbol in B, and then you can find the mutual information as H of B minus H of B given A. That's the better, because we already have H of B given A, so it suffices to just find H of B. H of B, we can use this method to do so. 1 over 5 times x plus 4 over 5 times 1 minus x. So H of B would be H of 1 over 5, 1 minus x, plus 4x over 5. Okay, so even if you're a little rusty like me, you can eventually work it out using this type of Venn, which hopefully means you're going to fare well in your exam. That's good. Unless I made a mistake. Yeah, so you can expand all this. You can get 1 over 5 plus 3 over 5x. So your mutual information would be, or specifically, first of all, your entropy for B would be this expression, using that function we spoke about earlier for H. And then if you subtract off the 4 over 5 we found for the entropy of B given A before, this would be your, now, was it before? That was B given A, yep, over there. And it's a typo here. Oh wait, yeah, I see. Because you can simplify this because these terms are the same, so this turns out to be just equal to H4 and 5. Yeah. So I think that shows up a few times in a question like this. So this turns out to be just your mutual information. Then finally, I believe this last question related to what we define as the channel capacity specifically is the maximum mutual information. So we are going to find that here. In this case, we're trying to maximize this function. And to maximize this function, you would want to use your chain rule because this entropy function, this H that we commonly use, is differentiable and has maximum value when x is equal to, you could say like that, x is equal to a half. Alternatively, you could say, actually, yeah, in this case, it would just be x equals to a half. Yeah, you just plug that in. If in a different case where you had like an x out the front here, you'd want to be a bit more clever in terms of using the fact that this has zero derivative when the input is equal to a half. But yeah, so this should be pretty straightforward. I guess you can differentiate if you want. Yeah, you can plug it in like this for h of x. You would get this expression for the derivative, and yeah, you would find that when x is equal to a half, then this is going to be 0, so the derivative is going to be 0. In other words, you want, you can do it like this if you want. Actually, yeah, no, that's, isn't right. You would want to use your chain rule. Oh yeah, you still plug in x is equal to a half.
I do this calculation since last year.
Yeah, it's probably better to just do it explicitly, or use the chain rule in some sort of fashion, but yeah, the difficulty here would be you would want to make, since you only have a constant factor out front of the derivative, you just want to, again, make this 1 over 5 plus 3 over 5 x minus 1 equal to 1, so we have 0 derivative. In other words, I just want to clear 1 over 2. Yeah, okay, I guess in this case, it still pops out x. And so that means this will become, you can find x, it turns out, in this case, interestingly enough, is still a half, but that makes this expression half. It should, because that's 1/5 plus 3/10, which is, oh yeah, it's still half. Yeah, that's still half. So it's equal to h a half, which is the maximum value of h. And so your channel capacity is 0.278. Okay. Right, so up to the next chapter. We might take just a little break for 1 or 2 minutes. So feel free to go over time or the time if you want.
That's okay.
Very much.
That's okay. Can I get just to wipe this, just the slides, because oftentimes LaTeX, not LaTeX, OneNote will lag if it has too many notes on it. So if I can just like have the rest of these in another like document or something, is that possible?
I'll just fix this screen for now. So in another document, you want like each section in another document? Oh wait, I think
Or just like if you can just put the document onto another OneNote.
Just like the last 3 sections in.
Yeah, I just need those in there. Just because it makes it less laggy.
Sure.
Because I remember last year I lagged a heckin' load, and I was constantly fighting.
Yeah, that's fair. I might just pause the screen. It's just okay. That should be good. Yeah, I'll just upload it from Overleaf. I don't think it'll lag too much, given that we only have half of them here. I guess yesterday wasn't too bad either. We had everything.
Sure.
Yeah.
No, it's just because like I'm gonna go. I'm gonna be writing. Gonna be writing a bit.
Share those friends. Okay, I'll comment now for TV.
Health first bit.
I started this for my just 3 years ago. So
Last week,
still
okay.
on top of my
Still the top of your brain.
yeah.
I know the last section is kind of everyone kind of a lot of people learn it from these slides. That's I remember that's what I did. That's what my friends have done. So I'm very conscious that some people actually learn the final topic from these slides and this presentation I'm about to do. So I want to make sure that I do it, well. And I've changed things up, made them a little bit slower, sometimes a little bit. I've made it a little bit. I like it better.
He worked on it very well. He's done some good work. Very part 2 to
2.2, 2.5.
Okay, let's put this in. Should be good. Just immediately.
Have you looked at this section of the before?
This part, yeah.
This some theory algebra down through to the next sections. What are the next sections? You've got number theory algebra. You've got
Algebraic encoding.
algebraic coding and cryptography.
Chapter 6 in particular.
That is fair. That's fair.
Chapter 6. Okay, so that would be
That's
Algebra.
algebraic coding.
comes a lot. Yeah.
Algebraic coding and cryptography. BCH. Yeah. Okay. So we'll go through an example of those today.
Okay.
BCH coding is really easy once you get the hang of it. Legitimately, it is. Once you do one example, it just kind of clicks. So I'm going to do one example. This was not done last year. Last year they decided to, no, actually, for the last 3 or 4 years, they've just gone through theory, which is sometimes useful. For this, I don't think it was helpful. So I've changed it up completely. I've rewritten the BCH code section. Hello everyone online. How many people do we have? Oh, 2 watching. Well, is one of those me? It might be. Okay, so this is lagging a little bit. So yes, hello and welcome to the second half. And hello people online and in the future who are not watching this live, who have maybe this is the section that they're like, oh no, I don't understand. So hello people that have just clicked over to this section. All right, so we're going to go through number theory and algebra. This is, unfortunately, this is kind of this section is going to be kind of long, and it's kind of almost a language section of the course. There are a lot of languages and a lot of definitions here, and unfortunately, that's kind of just what we're going to have to deal with. So let's have a look. The first thing that we want to talk about is the division algorithm. So let a and b be integers with b greater than 0. Then there exists 2 other integers. This is a quotient, and this is a remainder. Quotient and remainder, such that we can write A equals BQ plus R. So where does this arise from? This arises from what I can do is I can do A divided by B. I'm going to get a quotient, and I'm going to get an R divided by B. Right? Maybe we remember this from, or at least I did this in primary school. This is something that I have struggled with in primary school, so, it comes back. Unfortunately, everything always seems to come back. We say that Q is the quotient and R is the remainder. This is how we get the definition of modular arithmetic, right? So we have A is equivalent to R mod B. That means that A is equal to BQ plus R. Right, so there's some integer Q, such that if I multiply B by Q, it's going to be equal to R. I can add multiples of B, and I'm not going to change this equivalence relation. It also gives us the way of writing down this term factor, B divided by A, or B divides A, right? So B is a factor of A, B divides A. All right, next thing is the greatest common divisor. This is a section that, it's a thing that I'll show up time and time again. And really what we're trying to get from this is to figure out when things are co-prime, right? So let's see, what is the greatest common divisor? Suppose that A and B are integers. The greatest common divisor is the biggest number such that it is a factor of both A and B. And here's the Euclidean algorithm. So let's give an example of the Euclidean algorithm. Let's say that I wanted to find the greatest common divisor between 20 and 16. Now, we probably know what this is just by looking at it, but let's say we don't know. What I'm going to do is I'm just going to say, okay, 20 is equal to 16 times 1 plus 4. And then what I do is I look at this 16 and this 4 and I say, how can I break these two apart? Well, I know that 16 is equal to 4 times 4 plus 0. This plus 0 tells me to stop the algorithm, and then this number here, this 4, is our GCD. You can also extend the Euclidean algorithm to go upwards, which we will do when we do RSA. When we do RSA, we'll do an extended Euclidean algorithm. And actually, could I get somebody to pass me a paper that I had? Just now that I'm thinking about RSA. Yes, that's so I don't have to use a calculator later. Okay. No. I don't need to. So, now, again, this is a definition part of the course, so there's going to be a lot of definitions. I'm sorry about that, but it's the nature of the beast. An inverse. Let A be an element of Zm. So Zm, remember, is going to be the set 0, 1, up to m minus 1. Okay, and some element A in here has an inverse if I can multiply it in Zm and get 1. Okay, so for instance, if I had Z7, then, or Z10, sorry, let's do Z10. Z10, what is 7 inverse? What is 7 inverse? Well, 7 inverse is going to be 3. 7 inverse is equal to 3. Why? Because 7 times 3 is 21, and that is 1 mod 10. Okay, so 7 inverse is equal to 3. Kind of cursed looking at that, because I haven't written mod 10. All right, next thing, invertibility. This is a condition for when an element has an inverse. An element has an inverse if it is co-prime to M. So an element has an inverse in Zm if that element is co-prime to M. Okay, so this is what why we introduced GCD. The set of invertible elements in Zm is called the units. And the units are defined by this structure here, the GCD of A and M being equal to 1. Okay, so this is exactly follows from the equation up here. Right, this exactly follows. If M is prime, then every element is co-prime to a prime element. So everything except for 0 is a invertible element. All right, so Euler's phi function. This is certainly something that you're going to have to calculate at some point. And how you should think about it is you should think about it like this. Euler's phi function tells you, firstly, it's the number of units in Zm. That's how we're introduced to it. But how you should think about it is it's the solutions to this equation. How many solutions are there to this equation? GCD of AM is equal to 1. So A is between m minus 1 and 0, right? Because it's in AM. How many solutions are there to this equation? That's what phi of m calculates. Okay. So let's do an example of how to calculate a phi function. Let's do phi of 7,000. So phi has a couple of properties. It's multiplicative in coprime factors. So what does that mean? It means if I factorize this 7,000 into its prime elements, I can split apart my phi function. Okay. So I'm going to do that. I'm going to say, oh, this is 7 times 1,000, and this is 7 times 10 times 100. This is 7 times 2 times 5 times 25 times 4, which is phi of 7 times phi of 2 cubed times phi of 5 cubed. Yeah? All right. So then we can use our properties. Because 7 is prime, we can immediately say that this phi goes to 6 because there are 6 invertible elements in Z7. We have this property. If we have a power of a prime, then we can prove that all we have to do is take that power of a prime, subtract one of the powers off the power, and then subtract. So what we have is this is going to be 6 times 2 cubed minus 2 squared, 5 cubed minus 5 squared. So this is going to be 4. This is going to be 125 minus 25 is 100. This is going to be 6. 6 times 4 times 100 is 2400. Okay. All right. Euler's theorem. This is Fermat's little theorem, actually. Euler's theorem is a generalization of this. Fermat's little theorem says that if I have any number A that is coprime to P, and P is a prime number, then a to the P minus 1 is equivalent to 1 mod P. So you could say, okay, I'm going to have 2 and 7. So my A is equal to 2 and P is equal to 7. Then I know that 2 to the 6 is equivalent to 1 mod 7. This is also used in RSA encryption. But in RSA encryption, we actually use something a little bit stronger, which is Euler's theorem. So, hello. Euler's theorem is basically, hey, if I have a to the phi of n, then that is equivalent to 1 mod n. Maybe you will have seen proof of this historically. So, we also have to talk about primitive elements, remembering this is a kind of a this is a language part of the course, so there's a lot of definitions, so sorry about that. Order of units. So the order of a invertible element is that number which we have to raise the invertible element to in order to get 1. Right? So a to the k is equivalent to 1. This k is what we call the order of a. Okay? And it's the minimum such number. If you have, if you can take a and raise it to a power and get it equal to 1, then I could raise that power to the 2k, right? And that would be equal to a to the k squared, which would be which would be 1 squared, which would be 1. So it's not unique. We actually say it's the minimum one, and so therefore it is unique. All right, so that's what an order is. That's how many. It's the power. We also have to talk about what a primitive element is. This will show up in BCH coding. So a primitive element is an element that I can raise to the power, I can multiply onto itself many, many, many times, and I get my invertible elements. So a primitive element of so a couple properties. Firstly, its order is equal to phi of m. So its order is the same as the number of invertible elements. And that makes sense, right? If an element is primitive, and I can multiply onto itself to get every invertible element, then the order of that element must be the number of invertible elements, because I'm multiplying onto myself and I'm getting every single one. All right, so that's what a primitive element is. All right, here are a couple corollaries. This is, if A is an invertible element, then the order of any invertible element divides phi of m. What this means is that if I want to check if A is a primitive element, okay, I want to check that. Then what I'm going to do is all I have to do is I have to check if its order is any of the factors of phi of m, right? So let's say phi of m was equal to 15, right? So maybe we're in Z16. Oh, that's not right. Well, let's say phi of m is equal to 15. I only use this because that's what's going to happen in BCH coding. Then what we would have to do is we'd have to check if A has order 3. Is that equal to 1? Is that equal to 1? Is A to the 5? Is that equal to 1? If not, then we could say, oh, it's a primitive element. Yeah, if it's invertible and its order is not a factor of phi of m, then it must be invertible. Or 1. Okay. Primitive powers. If G is a primitive element, then G to the K is primitive when this GCD of K and phi of m is equal to 1. So this is saying that K is co-prime to the number of units. So if I multiply by K by itself again and again and again and again, it's going to take phi of m many times to get back to 1. All right, well, how do we count this? Well, what we said earlier is the best way to think of phi of m, phi of anything, is that it is counting the solutions to, it's counting the solutions to this equation. It says, okay, how many solutions are there to this equation? That's what phi of m means. That's what it means for an element to be invertible. And so this is what phi of m means. So if I look at this equation, I'm going to compare and contrast to what we have down here. Oh, we have, oh, it's the same equation. It's the same equation. So we get this corollary, which is that if um has a primitive element, then it has phi of m many primitive elements. Because phi of m calculates the number of solutions to this equation. Okay? I'm tempted to say any questions, but I know people are online. All right. Next section, primality testing. So the slides for this section were, actually they were wrong last year and the year before. I've corrected them. So let's have a look at this. So this is the definition of a prime number. Not super useful, but for those that are interested in pure mathematics, this will come up again when you take third year mathematics, third year pure math. And you look at it in a little bit more of a general sense. But what we're interested in is we're interested in trying to figure out if a number is prime. The reason that we're trying to do that is because when we do cryptography, figuring out if a number is prime is kind of important, right? So there are a couple of tests that we can do. So this is the pseudo-prime test. How it works is, remember Fermat's little theorem. Fermat's little theorem we covered just a little bit earlier, which was that a to the p minus 1 is equivalent to 1 mod p for p prime. So what the pseudo-prime test does is, let's say you give me an integer n, and I'm going to figure out if that integer n is prime. What I do is I call a witness to the stand, and my witness is called A. And he's going to say, I know n, and n is prime, or n is not prime. And this is actual math terminology. So this is actual math terminology. I didn't actually make up this court case example, but I think it's super cute. So if GCD, so what we're going to do, firstly, what we're going to do is we're going to say, okay, A, are you co-prime with n? And it better be, right? If it's not, then A would say, no. I divide n, and so n is definitely composite. Okay. Otherwise, let's say it is co-prime, so we've picked our witness well enough that we have to go on to the next test. And that's what we do, is we put these two numbers into Fermat's little theorem. Please. We say a to the n minus 1. Is that equivalent to 1 mod n? And if it is, then we would say, n is probably prime. So that's that written up. You can call witnesses to the stand. Sometimes it's the case that every single witness is a liar. And those are what we call Carmichael numbers. So 561, if you put it into the pseudo-prime test, you will always say, 561, that's prime. But it's not prime. It's divisible by 11. Because 5 plus 1 is equal to 6. So, I think it's like something times 11. I can't remember. But that's what a pseudo-prime test is. Next is the Lucas test. So Lucas's test says, this is actually a way that we can definitely say, hey, a number is prime. If this test tells you that a number is prime, then it is prime. Firstly, we have our n, and we have another witness, so we've got the same kind of structure going on, yeah? We do the same thing. We say, is A co-prime to n? All right, well, A is not co-prime to n in general. And then what we can do is we can put it into Fermat's little theorem again. And okay, now Fermat's little theorem is telling me it's probably prime as well, so we're going to add something else onto this. And what we're going to add onto it is we're going to check if for all primes that divide n minus 1, if this equation is true or false. If it's true, then it's 100% prime. If it is false, then the test is actually inconclusive. You can't take anything from the test. So let's do an example of this. Let's say n is equal to 7, and I'm calling my witness to the stand, and it's equal to 2. So, firstly, I'm going to check this one. GCD of 2 and 7. Is that equal to 1? Yes, it is. So it's not false. So I go on to the next one. Then I look at a to the n minus 1. So is a to the 6, is 2 to the 6, is that equivalent to 1? Mod 7. Well, yes, it is. It is equal to 1. So we go into the third thing that we need to figure out. What I'm going to look at is I'm going to look at the prime factors of 6. So prime factors of 6 are 3 and 2. Then what I'm going to do is I'm going to look at this equation, looking at this guy, and I'm going to say 2 to the 6 divided by 3, is that equivalent to 1? And 2 to the 6 divided by 2, is that equivalent to 1? Okay, so 2 to the 6 divided by 3 is 2 to the 4. And this is 2 to the 3. Is that equivalent to 1? Mod 7. So, 2 to the 3, that's equal to 8. So actually this one is true. And this one is 16, which is 2 more than 14. So it's not true. So how do we interpret this? Is we go back to this dot point and we say, well, it is not true that for all primes, it's not equal to 1. So that means I found a 1. I found it's equal to 1 somewhere, and therefore my statement is inconclusive. My statement is false. And therefore, my test is inconclusive. Because I have found that when I raise 2 to the factors of my primes dividing out n minus 1, I get a 1 sometimes. That means Lucas test fails. Okay? All right, and that's what we did. All right. The second to last factorization or primality test is called the strong pseudo-prime test. And what we do is let's just go through it really quick. Let's say I have n is equal to 97. 97 is not really famously, but kind of it is a prime. What we're going to do is we're going to follow an algorithm. This is the steps of the algorithm. Look at n minus 1. This is 96. And I'm going to divide it by 2 as many times as possible. And so what we will see is that this is actually equal to 2 to the 5 times 3. It's 32 times 3. Okay? So I know that n minus 1 is equal to 32 times 3. That means n is equal to 2 to the 5 times 3 plus 1. Okay, so n is equal to 2 to the 5 times 3 plus 1. That tells me that s is equal to 5 and t is equal to 3. Okay, so far so good. Right. Then what we have to do is we have to do a couple of checks. So we haven't called a witness to the stand yet, so let's do that. I'm going to call a witness A is equal to 2. 2 is my favorite witness. It's not 1, which means it's not too simple, but it's 2, which means it's simple enough for me to do without having to get a calculator. So what we do is we look at is 2 to the 3, is that equivalent to 1 mod 97? Well, it doesn't even get up to 97, so there's no chance. So if it was equal to 1, then we would say, oh, it's probably prime. But it's not. So we have to go on to the next step. And the next step says, hey, what you want to do is you want to check for every element R, if there exists some value of R such that a to the 2r t is equivalent to -1, then n is probably prime. Otherwise, it's not prime. So I'm not going to prove this. This is probably done by Thomas Britz, but I'm just going to show you how to use it. So what we have to do is we know that R goes from 0 to s minus 1. So R is an element of the set 0, 1, 2, 3, 4. And what we have to do is we have to check if 2, which is my witness, to the 2 to the 0, t, is that equivalent to -1? 2 to the 2 to the 1, t, is that equivalent to -1? 2 to the 2 to the 3, t, 3, that t shouldn't be in the bottom, is that equivalent to -1? And what you will find is that when r is equal to, I think, 3 here, you put it into your calculator. So I think you've got a Desmos calculator or some kind of kcal. That should be able to tell you, hey, this is equivalent to -1. And so the test succeeds. We found that 97 is probably prime, which is good because 97 is probably prime, is actually prime. So we've succeeded. Our test has gone well. There are some numbers, though, that are called strong pseudoprimes that this test will fail for. So this is, again, a probably prime test. It's not like the Lucas test, which was definitely prime. This is a probably prime test. The next one is Fermat factorization. Fermat factorization is a way of factoring big numbers. Yo!
I think there might have also been two checks you have to do for it to be strongly pseudo prime. The GCD check and the Fermat's little theorem as well.
Yeah. So is that actually included? So is the Fermat's little
lecture slides? It's kind of like buried in the body of the.
Oh, sure. Yeah. Yeah. So the question was, hey, don't we have to do the Fermat's little theorem check and the GCD check? And yeah, probably. Is that buried in here somewhere? I'm not sure. But I think it is in the lecture notes, as you said. So yes, actually, there should be two other things here, which is do your Fermat's little theorem check, and do your GCD check. Okay? Cool. So now what we're going to do is we're going to do Fermat factorization. This kind of factorization technique applies when n is suspiciously close to a big square number. So here, n is equal to 2,419. That's suspiciously close to 2,500, which is 50 squared. So what we're going to do is we're going to actually rely on this equation here. S squared is equal to t squared minus n. What we do is we take the square root of n and take the ceiling of that. Okay? So the square root of 2,419 turns out to be a little bit more than 49, which means that this square root is going to be 50. Okay? This ceiling is going to be 50. And so t is going to take values from 50 all the way up to 2,419. And for every single one of those values, what you want to do is you want to calculate s, which is equal to the square root of t squared minus n, for every single t value. If this s is an integer, hooray, we're done. We can factorize. So what we do is we could say, okay, let's look at this. Is 50 squared minus 2,419, is that an integer? Well, it's equal to 81, which is 9. So s is an integer. Hooray! Since s is an integer, we can take our fundamental equation, s squared is equal to t squared minus n. We can take the n over to the other side and the s. So we can have n is equal to t squared minus s squared, which is equal to t minus s, t plus s. We know that t is equal to 50, and we know that s is equal to 9. So we know that n is equal to 41 times 50. Make sense? No questions in the chat. It's good to see. All right. So, hooray, we're done with factorization stuff. Unfortunately, we're still in the language section of the course, so there's some more stuff that we need to handle. So, what is a field? A field is a set of numbers that kind of act like scalars, and they behave nicely under like kind of scalar kind of stuff that you would want to do with scalars. So you can add, subtract, multiply, and divide them. And there are generally a lot of rules for what a field is. So if you have two elements in the field, you can add and multiply them, and you'll still be in the field, right? So you should get like kind of senses of kind of like a vector space thing happening. You have associativity, so that means we can change around my brackets with both addition and multiplication. We can commute elements, so it doesn't matter. 2 plus 1 is the same as 1 plus 2. 2 times 1 is the same as 1 times 2. You'll also have identity elements. So that means that there exists a 0 element, such that if I add 0 onto any number, I will get the same number. So this is an additive identity. And it has a 1. So if I multiply any number by this 1, it's a multiplicative identity, I get x. There are also negative elements. That means that if I have an element in my field, let's say 3, there's negative 3 is also in my field. I can add them and I can get 0. There are multiplicative inverses, right? So if we were in Z10, remember at the beginning we said that 7 was equal to 7 inverse was equal to 3. So if we're in Z10, if this were a field, then 7 and 3 inverse. 7 and 3 would both be in the field. Of course, we're going to see that I don't think Z10 is a field. Okay, so we also have distributivity under addition and multiplication. So that means, hey, we have all these things from high school where we can distribute numbers nicely and go through brackets and et cetera, et cetera. All right. The reason that we go through this is because we want to introduce the idea of a finite field. So usually when we think about fields, we're thinking about like R, we're thinking about C, we're thinking about Q. These are all fields, but they're all infinite. They all have infinitely many elements. Finite fields are the exception. These are fields with finitely many elements. And these are very nicely classified. So firstly, ZP is a finite field if and only if P is prime. So earlier I had Z10. This would not be a field. You would be able to find some kind of contradiction between the axioms and Z10, not a field. All right. And this is the nice thing about fields. So generally in mathematics, what happens is when you see a new object, you should ask, how do I classify that object? That's generally a true fact about mathematics. And that comes from category theory. But this is how we classify finite fields. So here's a fact. This is really a theorem definition. Every finite field must have an order prime to the nth power. True fact. And fields of the same order are isomorphic to each other. Isomorphic is a fancy word that I'm sure a lot of the first years would never have heard of. What it means is that the fields they look the same to relabeling the elements. So if I multiply 2 elements and I get a third element, if I just relabel the elements, that kind of relationship doesn't change. That means that these fields kind of look the same to each other. And any field with order p to the n, they look kind of the same to each other because they have the same order. That means we actually are able to write this sort of equal sign. Every field F with a finite, very finite field can be written as Galois field of Pn. This is just saying it's a finite field with Pn many elements. Okay, so you'll have 0, 1, up to Pn. So you'll have 0, 1, some primitive element alpha up to alpha to the p to the n minus 2 because we have a 1 and a 2. Okay, so next thing, polynomials. We all know what polynomials are, right? So polynomials are just, oh hey, we have polynomials. We've done so much of this in high school. If an is equal to 1, then f is called a monic polynomial. If an is non-zero, then the polynomial has degree n, right? So if it was 0, then you wouldn't even have this term, and we'd just say, oh, it's degree n minus 1. And the set of all polynomials over f is denoted by f and then these square brackets x. This is what we call, and maybe someone will correct me because I'm only a mere physicist, this is what we call a field extension. What it is it says, okay, we have our field elements. These are our scalars, right? And what we do is we extend it with x. X is some unknown value, and we're going to write polynomials or words, x to the 1, x to the 2, x to the 3, x to the 4, and so on. And this is what we call a field extension. Interestingly, it is also the way that we define complex numbers, but that's a question for another day. Unless you already know, I don't know where you're up to, man. So, but we're using it to just mean, hey, it's a set of polynomials with scalars in our fields. Okay, so there are a couple things that we would like to have with our polynomials. We'd like to be able to divide them. So, if f and g are our polynomials with scalars in our fields, and g is a non-zero element, then we can do polynomial division. That's what this says. We also have the remainder theorem. The remainder theorem is basically what we do is we say, hey, if we divide by x minus c, we're going to have some remainder, which is equal to f of c, and we're going to have some quotient q of x. The reason that this remainder is f of c is because if I put c into here, we're going to have q of c, c minus c, plus f of c. This is going to go to 0, and so we see that the remainder is just f of c. All right, and this is for some unique polynomial q. So this is all we're saying, is what we're saying, hey, we can divide, right? Maybe you did this in high school, maybe you didn't. Right, but really what we want to say is we want to retrieve this information from the remainder theorem. And this is the factor theorem. Monster energy break. What it says is, hey, if this f of c, if the remainder is 0, then c is a root, right? So this is something that we used extensively in high school. We said, oh, if my polynomial has 2 as a root, gets equal to 0 when I put 2 into it, then 2 is a root of that polynomial. Same thing here. The next thing is irreducible polynomials. So a polynomial is irreducible if it can't be factorized in f of x. So an example of this is x squared plus 1 in r extended by x. So r was a field. And, well, it doesn't have any complex numbers in it. So we actually can't factorize this into, well, we could try x plus 1, x minus 1, but that wouldn't work, right? We really had to introduce the square root of minus 1 to deal with this, yeah? All right, so this is what it means for a polynomial to be irreducible. It kind of looks like this x squared plus 1 if you haven't introduced complex numbers yet. So we want to figure out, is this polynomial reducible? Can we reduce it? Can we find factors? Well, the easiest thing to do is to look at Z3. And the funny thing is, with finite fields, there are only so many scalars that we have. So we can just test them all, right? If we could test every real number, then we could find the roots. What we're just going to do is we're just going to test every number. So we're just going to do f of 0, f of 1, and f of 2. All right, well, f of 0, this is going to be 1. It's not 0, not a root. F of 1, this is going to be 1 plus 2 plus 1 is 4. We're in Z3, so this is equivalent to 1. Ah, not a root. Oh no. Is this one a root? Well, what we can do is we can test, this is 4 plus 1. Is that equivalent to, that's equivalent to 9, which is equivalent to 0 mod 3. So, 2 is a root. So that means we can factor x plus 2 plus 1, x squared plus 2x plus 1 has a factor of x minus 2. But we couldn't just break apart a quadratic into just one factor. There has to be another factor. And we figured out, oh, none of the other ones are roots, so the only possibility is this. We found a factorization just by testing everything. Okay, well, let's see if are we right. So this is x squared minus 4x plus 4. Remember, negative numbers and modular arithmetic. This is actually x squared minus 6 plus 2, right? It's minus 6 plus 2, which means this is going to be equivalent to 2. So this is going to be x squared plus 2x plus 1 mod 3. Okay? All right. And this is just what we say here. All right, so that's what it means for a thing to be irreducible. I only go through that because we're going to see a lot of theorems where it's like, if this polynomial is irreducible. And I just wanted to make sure that we know what that is. Something to note is that if your polynomial is of degree 4, it can actually be split into 2 quadratic factors, right? So in that case, you can't test all the roots because you can reduce it, can be broken apart, but it might not have any roots. So in that case, what you'd have to do is you'd have to do some kind of polynomial division or guess at the polynomial. For Z2 and Z3, there are actually very few irreducible polynomials. And there is a list of these on Wikipedia. Okay, so I think there's like 3. So you just have to test each of those. And I'm sure in a question, Thomas Brits would give you, hey, is this irreducible with this polynomial? And then you just have to do long division, right? Polynomial division, yeah? All right, polynomial modulo. A set of polynomials, modulo f, is denoted like this. So what we're doing is we're saying, hey, we have our polynomials. And then what we have is modulo f means that our f function is equal. Let me restart with that. Polynomials mod f. What that means is that what we've done is we've subtracted off f as many times as we possibly could. Right? Remember when we said that a was equal to a plus bq was equivalent to r. We have b many copies of the quotient. And we're just subtracting off. We have q many quality. Yeah, we have the quotient many times the modulo element, right? That's qb was mod b. So we have q many b's. So we're just going to subtract that off from a until we get the remainder. Yeah. Same thing happens with modulo arithmetic. You have q many copies of f, and you're just going to subtract them all out. Make sense? I see nodding. Oh, here's a question. Oh, okay. No questions. That was just Brandon. Okay. I'll do an example of this as well later. So if that didn't make super much sense, we'll see an example. Finite field theorem. All right. Big theorem time. This is the theorem for this part of the course. If P is prime, and M is monic and irreducible in ZP, so it can't be factored in ZP and it's monic, of degree n, and alpha is a root of mx, this should really just say mx, it's a root of mx, so m of alpha is equal to 0, then this guy is a field. This is a field, and it has certain properties. First property is that it's a vector space. So why do we care about this? We care about it because then every element, non-zero element of the field, can be written as linear combinations of the roots of that monic polynomial, the roots of that polynomial that we're factoring out. So that means that our fields can be written as 0, 1, alpha, alpha squared plus alpha plus 1, alpha, maybe there's a cubed term plus alpha plus 1, maybe there's not even an alpha squared. You just get every single one of these. That's how we can write arbitrary fields in terms of the factors of this polynomial. There are p to the n many elements in this finite field, which just means that, hey, we have gf of p to the n. And there also exists a primitive element. So there exists a primitive element of order p to the n minus 1. Why is it p to the n minus 1? The reason is that when you're multiplying alpha by itself many times, you're never going to get 0. So if there's p to the n many elements in our field, then there's going to be p to the n minus 1 elements that we can hit with a primitive element by multiplying the primitive element onto itself, right? Remember, that was the definition of a primitive element. We could multiply the primitive element onto itself and get the invertible elements. And in a field, every element is invertible. Does this make sense?
Apart from 0.
Apart from 0, yeah. So actually, that's part of the definition of the field. 0 is not invertible. Yep.
The thing that's meant by the minus 1 is that
Yep.
0 is not.
That's right. So 0 is not. So that means when we're looking at something GF16, what we're going to have is we're going to have 15 elements that are invertible, right? Because 0 is not invertible. Make sense? Awesome. And so if something doesn't make sense and you're looking through these slides, come back to this, right? This is the big theorem. Everything comes from here. Oh, and this is the element that we're looking at here has order p to the g to the p n minus 2, because we're saying that g to the p n minus 1 is equivalent to 1. And yeah. If I multiply this element by g, I'm going to come back to 1. So there's kind of a cycle going on here where g squared, g cubed, and then I have to go up to g to the p n minus 2. So I have, and then I can get to 1, which I have not counted yet with g. Okay, so moving on. Primitive polynomial. A polynomial is primitive if it is irreducible and its root is primitive. Okay, so its root has p to the n minus 1 order. Here's an example question. So sorry about this. There was a lot of definitions there. It's just kind of part of the course. This is a really good. It's really good for a lot of the pure math students. The higher year subject is very much, for higher year algebra, is extremely an language course. And you're going to see many of the definitions that we are seeing here pop up again and again. We're not going to look at finite fields there, but for you pure math students, this is actually a really good course to just kind of wet your feet and see if you like the subject. So here's M1. Let M1 in Z2X, so our polynomials have coefficients 0 and 1. You may assume that M1 is an irreducible polynomial. Okay, good for us. We don't have to factorize it. It's x to the 4, so we would have to factorize it into 2 quadratics maybe. Yuck, don't want to do it. Is an irreducible polynomial in Z2. And let alpha be a root of M1x. Find a description for the non-zero elements of this field. All right, so there's 2 ways you can do. Yo.
Why would we need to factorize it?
If it wasn't irreducible, why would you need to factor it? Because the finite field theorem requires that M is irreducible. Yeah. Okay, cool. So remember, if something's confusing, finite field theorem.
So it would be a field that was increased.
Exactly. So find a description of the non-zero elements. So there's 2 ways we can do this. We can just, we know that, alpha is a root. It means finite field theorem tells us that the field is a vector space in alpha, powers of alpha. So that means we can write every element of the field as just 0, 1, alpha to the 1, alpha to the 2, alpha to the 3. All right. So we're just going to have every combination of these, and that's going to give us our finite field, because it's a vector space in those elements. It's not alpha to the 4, because we're modulo x to the 4 polynomial, so we're always going to subtract off an x to the 4 term. Remember, modulo m1 means we're subtracting off everything x to the 4th. So that's x to the 4 is always going to be 0. You're only going to have x cubed terms. Simplify. So that's one way we can do it. There's actually another way. And that is, you can know that this M1 polynomial is also a primitive polynomial. There are, I think, 3 of these. This is one of them. And so what you can do is you can just write out a table. This table is all of the powers of alpha. Okay? And so now this table is really useful. I can look at alpha to the 8, and I can go up to my table, and I can say, oh, it's alpha cubed plus alpha squared plus alpha. We're in Z2, right? Because that's what the field was. So these are going to cancel. And we can do the same in the bottom with this alpha to the 11. This alpha squared is going to cancel with this because we're in Z2. And so what we are going to be left with is this term. Use our table again. Go back up. And we can see that the top term is just alpha to the 11. And the bottom term is alpha to the 4. Okay? So actually, it's worth doing just really quickly. It's worth teaching you how we can generate this table. So we start with alpha to the 0, which is equal to 1. Then we multiply that by alpha. Then we multiply it by alpha again. Then we multiply it by alpha again. And then we multiply it by alpha again. We're getting a pattern, right? So we get alpha to the 4. But because we are modulo this polynomial, we know that any x to the 4 plus x cubed plus 1 is equal to 0. And so in particular, that means that alpha to the 4th plus alpha cubed, oh no, this is plus 1, is equal to 0. I'm getting lag because I'm writing so much. And that means that alpha to the 4 is equivalent to alpha plus 1 because we're in Z2. Cubed plus 1. Okay. Right, so we go through this, and we can just find a solution for alpha. The next part of this question was to row reduce. Row reduce is very simple. All you have to do is remember first year, and what we can do is we can, including,
solves the linear equation.
yeah, solve the linear equation.
I didn't even bother because I just read out alpha of x plus
You can do that. You can do that. You can just solve it like just exactly. What you can also do, though, to make things simpler on yourself, is you can just use the reduced row echelon form. Yeah. So this is how you would do that. I'm not going to go through it because I'm already running out of lag with my notes. So let's see. All right. So actually, I'm going to speed up quite a bit. So the next thing is alphabet coding. Can I get a can I?
all back off.
Yeah, no, I just this is starting to lag. I think I have to delete everything, but can I do that real quick? Yeah. So I'm gonna have to delete all of this junk.
There is probably this control on it.
Yeah, if I do Control A, it's gonna copy everything though. This is getting on. This is like actually hard.
Solves.
Should I get the notes as well?
Doesn't.
That's it.
I think. What if I do this first? Part of the issue is because we had this thing in.
I think it's because I'm writing so much. It's extremely
True. They don't keep better than things.
alright. It's like pause. Yeah, that's what I mean. I'm sorry.
Okay, that's better. Yeah.
Oh,
That's all just in the back.
okay. Codes, minimal polynomials. This is our next section. Algebraic coding. All right. Brief pause. Back on top of things. Okay, algebraic coding. This is the next section. The way that we're going to structure going through this topic is we're going to do the following. We're going to go through theory, and then we're going to do one example. And that's it. This topic is actually very small, but it's kind of intimidating. There's also Problem 86 on YouTube. Problem 86 on YouTube is sensational. It's a sensational video. Go through it. It'll also make this next section make a little bit more sense. But first we're going to go through a little bit of theory. So, first thing
is we've looked at Hamming codes before, but we're actually going to redefine them here. We're going to just jumble up the order a little bit. The way we're jumbling up the order is, let's say we have a Hamming code. It's a 7-4 code, clarity check matrix, and it's arranged in this way. 1, 1, 1, we get our leading columns first, and then it looks a little bit weird here. What these correspond to is it corresponds to alpha to the 0, alpha to the 1, alpha to the squared, alpha cubed, alpha to the 4th, alpha to the 5th, and alpha to the 6th. So, in particular, if we look at this is our minimal polynomial. If that's our minimal polynomial, then we can generate one of those tables that we did before, right? And so, what we would find is if we generate this table, alpha cubed would be equal to alpha plus 1. Okay? And so, each of these columns, this is representing the 1's unit, this is representing the alpha unit, and this is representing the alpha squared unit. Okay? So that's what how we're going to reorder our parity check matrix. And alpha is a primitive root. Okay? This is going to be the main difference between what I do here and what Thomas Britz does. The columns of H correspond to coordinate vectors, so that's exactly what I said. And we can also represent H with 1, alpha, alpha squared, alpha cubed, and if we just write this, then we're saying exactly the same thing. Okay? In BCH coding, sometimes if we want 2 error correction, we're going to stack 2 parity check matrices on top of each other. And so, we're going to tell you how these alpha and betas come up and what they are, but for now they're just 2 different primitive elements kind of related to our field in some way. Alright, so how many non-leading columns does the parity check matrix have? This is a motivating question, because as it turns out, we are going to, the non-leading columns are going to correspond to the information, the message that we want to send. And the leading columns are going to correspond to the redundant armor we're putting on our information. Yeah? So, how many non-leading columns does it have? Well, alpha and beta, alpha was, so this top one, what it looked like is it looked like this. And there were 3 leading columns and 4 non-leading columns. If we put a beta below it, we're going to take up 3 more non-leading columns, and we're only going to be left with 1 information column. Okay, 1 free column. Okay, so this is just something just to be comfortable with. When we have a code word, how BCH coding works is we're going to have some polynomial that we're associating to the code word. So let's say we get the polynomial C0, C1 up to C6. What we're going to do is we're going to generate this polynomial. This is called the code word polynomial. And what we do is we take this C0 and we put it into this. We put it over here. With C6 comes down and goes over here. Make sense? So this is like the beginnings of our strategy for BCH coding. If this is a valid code word, then we can calculate the syndrome of our code word, right? So we have our parity check matrix, H, and we can multiply it by our code word, let's say like 1, 0, 1, 1, 0, 1, or so forth. These would multiply across, and you would get, if it's a valid code word, then we define the syndrome to be equal to 0. Yeah? Okay. And of course, we can represent this parity check matrix in terms of the alphas, and so therefore, C of alpha is also equal to 0. That's actually another way of saying that we have a valid code word, is if C of our primitive element is equal to 0. I haven't told you what the primitive element is yet. Patience. So, where does it come from? That's a question that should be at the top of your mind. This is another thing, just explicitly writing out that, hey, we have an information polynomial and a check bit polynomial. Okay? So, let's talk a little bit. So that was one section, one of the preemptive things that we needed to cover. Now let's go to the second one. So there were three things that I wanted to cover before we go straight into it. Minimal polynomials. Given any element, beta, there exists a unique monic polynomial such that m of beta is equal to 0. And m has minimal degree. So what is a minimal polynomial? It's a polynomial with respect to some element of the field that is irreducible and of minimal degree. Okay? And it has a root of beta. So I say, okay, here's my element of the field, beta. I say beta, and then somebody will say, here's a polynomial. It's monic, it's got minimal degree, it can't be broken up, and it has beta as a root. Okay. Here's a theorem. If beta was a primitive element of our field, then its minimal polynomial has degree n. We can use that to check if a polynomial is minimal. What we do is we look at this polynomial, and this was a polynomial we saw before. We actually looked at its root, and we expanded out the whole table. It's the same polynomial. And what we found was that alpha had order 15. Had order 15. Now, our field is Z2, and this F is order 4, which means we're going to only have polynomials, x cubed, x squared, x to the 1, x to the 0. That means there's going to be 16 elements. Or rather, another way of saying it is that this is GF 2 to the 4. Okay? Alpha is the minimal polynomial, so there is 2 to the 4, which is GF of 16. Alpha is order 15, which means that alpha is primitive. If alpha is primitive, then its minimal polynomial has order n, and n is equal to 4. All right. So we also have that this is a unique polynomial, and so therefore we can conclude that this polynomial is actually a minimal polynomial for alpha. Right. We can actually state that out a little bit explicitly there. I'll give you a moment to read if I didn't make sense. All right. Cyclotomic cosets. This is our third thing, and then we can go and start looking at a problem. Let alpha be a primitive element of some finite field. Suppose that f has root alpha to the s. So we have a primitive polynomial. Alpha is a primitive element of some finite field. And suppose that f has a root alpha to the s. Then this is the cyclotomic coset theorem. It says, if alpha to the s is a root, then I can multiply that power by p, right? So I can multiply by p, and I can multiply by p again, and I will end up generating all of the roots of my polynomial. So let's look at an example. And we call the set of these powers the cyclotomic coset. The term coset here comes up in pure math. And what it means is, something that's interesting about it is that if you have two different cosets, if they share any element, then they must, one must contain the other. So you can imagine, hey, if alpha to the s was equal to alpha, there's a containing relationship, which means no two cosets are going to contain the same element. Anyway, suppose that beta is the root of some monic polynomial, then I want to express the other roots in terms of beta. So the only thing to do is to say, okay, well, what is my p? My p here is 2. Okay? This is my zp. So if I have x minus beta as a root, I also have x minus beta squared as a root, x minus beta to the 4th as a root, and x minus beta to the 8th as a root. I also would have x minus beta to the 16th. However, this polynomial is an x to the 4th polynomial, which is another way of saying that this is gf of 16. That means that our primitive polynomial to the power 15 is equal to 1, so this is just the same as beta. You can also read that straight from the theorem. And so we don't have to consider this at all. All we have is that we can represent our polynomials in terms of this set. So this is a factorization of our polynomial. Okay, there's a lot of stuff here. Let's now get into an example. So, example encoding for BCH codes. So here's a question I. using the finite field, f, and this is our finite field, a double error-correcting BCH code is constructed. Find a primitive element of f, and hence find a description of the non-zero elements of f. So, find a primitive element. How do we do it? Well, we just have to find an element with order 16 minus 1. So, what we could do is we could start guessing. And you could guess, oh, maybe the primitive element is a root of this polynomial. And if you do that, you would have alpha, you would write up your table. You'd have alpha 0 is equal to 1, alpha is equal to alpha squared is equal to alpha squared, alpha cubed is equal to alpha cubed. And then you get to alpha to the 4. And this would be under x to the 4 plus x cubed plus x squared plus x plus 1 is equal to 0. We're in Z2. And so that means that x to the 4 is actually equal to x cubed plus x squared plus x plus 1. So this would be alpha cubed plus alpha squared plus alpha plus 1. All right, let's look at alpha to the 5th then. This would be alpha to the 4 plus alpha cubed plus alpha squared plus alpha. Then I have to simplify this alpha to the 4th, but what I would see is, oh, alpha to the 4 is alpha cubed plus alpha squared plus alpha plus 1. And so alpha to the 5 is equal to 1. It's not primitive. Okay? So we can't just guess the root of that polynomial we're given to be the primitive element. We have to pick some other element. So what's another element? Well, 4 plus 1 is another element. Remember, our field is a vector space, so we can add elements however we wish. So what you can do is, if you guess gamma is equal to alpha plus 1, then you can generate this table. This table is super important. Maybe everyone will take a picture of it because I'm going to be referencing it, and just because of the format of this talk, I can't take this with me. Okay? Okay. Cool. So, use this. Man, I'm abusing your laptop, man. Brandon, I'm abusing it so bad. Encode this message using BCH coding. The way we do this is we need to construct our code word polynomial. So if we had a real message, what we would do is we would start reading off our message, and we would just say, oh, the coefficients are going to be the message, a real code word. We could write down our code word polynomial just by transposing the elements of the code word onto powers of x. We've got a message though, and so this message is our information part of the code. So that means it's going to correspond to I to the x. Now, I to the x, or I of x, is actually going to look like this. It's going to look like I of 8 plus I of 9. So what I'm doing is I'm saying this 1 goes here, this 1 goes here, this 1 goes here, this 0 goes here, this, and so on and so on and so on, right? Why is it x to the 8? The reason that it is x to the 8 is because of the leading columns of our matrix, of our check bit matrix. We have 2 error correcting, which means that there is two rows to our check bit matrix. Remember, this is the alphas and the betas, and each alpha is going to be 4 down. So there's going to be 8. It's going to be 8 bits, which are for armor, and there's going to be the rest of them for information. So 8 bits for armor. That means that we have to the 1 up to x of 7. This is our armor, and it's I to the 8 to the rest of them. Anyway. Magic, please. Oh no.
Okay, my bad. Sorry about distribution.
It's this way. Alright, so this is finally about to start coming together. After the polynomial with our information bits and then check bits. So how do we form the armor? How do we form the armor around our code? And this is how we do it. We have our armor is equal to I of x, our information, mod mx. So what is mx? Well, mx is going to be, we're going to multiply two minimal polynomials with different sets of roots. And so this one is going to have root alpha, and this is going to have root beta. Okay? And so we have to find two minimal polynomials with different sets of roots. Okay, so how do we generate one of them? Well, we can generate one of them just by saying, oh, we want this minimal polynomial to have a root gamma. And then the cyclotomic coset theorem tells me, oh, if it has root gamma, then it has root gamma squared, gamma to the fourth, gamma to the eighth. So I'm going to know that MA is equal to x to the gamma, x gamma squared, x gamma to the fourth, and x gamma to the eighth. Right, well, I want my other polynomial to have different roots. Right, this is our how we start constructing BCH coding. And so I'm just going to pick, okay, well, maybe it has a root gamma cubed. Because this is cosets, nothing will ever overlap. So we would get gamma cubed, gamma to the 6th, gamma to the 12th, and gamma to the 24th. Gamma to the 15th is equal to 1 because of the table. And so therefore, gamma to the 9 is our final root. And so MB is going to be x minus gamma cubed, x minus gamma squared, and x minus gamma 12 cubed to the 6, and x minus gamma to the 9. Alright, so those are our two minimal polynomials. That lets us form mx. Mx, we just multiply these two together. And unfortunately, this is a heck of a calculation. It's a heck of a calculation. You have to multiply those two polynomials together. And not just those two polynomials, you're going to have to multiply the gammas out. And remember, the gammas from the table are written in terms of alpha. And alpha is mod 2, right? So multiplying these out together, it's a heck of a calculation. I'm sorry about it, there's nothing to be done. Actually, you could multiply these out just raw. You could just say, okay, I found my two polynomials. Multiply them together. Mod 2. Okay? And that's how you generate this add. And so, by definition of our BCH coding theory, this R of x is going to be I of x mod m of x. And so, you can take your I of x polynomial, which was thing x to the 14, and subtract off multiples of this x to the 8th polynomial. If you do that, you will find that this R of x is x to the 6th plus x squared plus x plus 1. Okay? So, and that, we're done. This is our encoded message. We found our code word polynomial from R of x plus I of x, and then we can just say, okay, what are the scalars, what are the coefficients at the front, and those form the bits in our message. All right, so that's encoding. Next up is decoding. So I give you a message. Decode this message, please. So how are you going to do that? Well, first thing to do is, well, if we've got any message, we should calculate the syndrome, right? If it's equal to 0, then maybe it's a real code word anyway. So we're going to calculate the syndrome. Oh, by the way, I didn't tell you this. The roots, h, this was 1 alpha squared r2 alpha to the 14th in this case. The other roots, this is a minimal polynomial. It's gamma, it's gamma. It's not alpha, it's gamma. It's going to be gamma, 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 gamma. The other ones are going to be gamma cubed because we choose gamma cubed to be our other subatomic coset root. So it's going to be gamma cubed, gamma to the sixth, up to gamma to 42.
The elements of this matrix polynomials, or is it the binary expansion matrix?
It's the binary expansion I showed earlier.
So this is just the left hand running it.
Yes. So it's either these are the primitive elements, and so we're going to be running everything in terms of primitive elements. Most of the time, if you're lucky, if you get a nice polynomial for the modular polynomial, the alpha is going to be a primitive element, and so that makes this a little bit nicer as well. But you'd still have alpha cubed, alpha to the sixth, alpha, and those would be again expansions. Yeah. Because alpha to the sixth, right, would be like alpha cubed and something like that.
So the rows is still basis.
So rows, yes. So the rows are, it was our minimal polynomial MA, and this was the root of that minimal polynomial MB. Yeah. Cool. Makes sense? Feel confused still.
I think so. But if you write that in full, it would be really long,
It'd be really long, yeah.
and each row corresponds to
If it would be really long, and each row would correspond to, yes, but you have two blocks. Yeah, you have two blocks. Alpha, you have alpha to the 0, alpha to the 1, alpha cubed, alpha to the square, and then alpha cubed. And you have again alpha to the 0, but this is for these. This is next set. Yeah. Okay. So, what we can do is, as with any time that we calculate try to decode something with a parity check matrix, we calculate the syndrome. And the syndrome, what you can do is you can just multiply your parity check matrix by your dt, and you're going to get two polynomials in gamma and gamma cubed. All right. It turns out if you do this, you're going to have this corresponds to x to the 1, x squared, x cubed, x squared, and so on. You get this d of x polynomial. And you can calculate d of gamma and d of gamma cubed, right? We can just expand d of gamma because we have every power of gamma in terms of alphas. So if we expand that polynomial, and unfortunately, ugly again, but what it'll come down to is it'll come down to something really nice. It'll just be gamma to the 4th. And d of gamma cubed will also expand and it comes down nicely, although in this case what you can do is you can say that gamma to the 30, that's equivalent to 1. We're in mod 2, so gamma to the 30 is going to cancel with that 1. Gamma to the 36 is going to cancel with this 6. And so that makes it a little bit nicer. But we're still going to have alpha cubed plus 1 as the expansion, and that's down to the 8th. Okay, so we've done this expansion. What do we do next? How do we figure out where the error messages are? And this is how we do it. We look at the syndrome, and we classify it into 3 categories. So the syndrome is equal to 0, well, it was the valid code word the whole time. If it's not equal to 0, then there are 2 cases. Is d of gamma cubed equal to d of gamma all cubed, or is d of gamma cubed not equal to d of gamma all cubed? If it is equal to d of gamma all cubed, then it's 1 error. If it's not equal, it's 2 errors. So, what was it for us? Well, for us, we had d of gamma was equal to gamma to the 8th, and d of gamma cubed, no, d of gamma was equal to gamma to the 4th, and d of gamma cubed was equal to gamma to the 8th. Well, 4 times 3 is 12. 12 is not equal to 8, so we've got 2 errors going on. And so we have to figure out where they are. So I've introduced my d polynomial is equal to a true code word plus some error in the ith position and some error in the jth position. If I turn these into polynomials, then I'm going to have an x to the I and an x to the j. Right? The real magic is when you put gamma into these polynomials, this true code word polynomial. If you put gamma into it, that just means gamma goes to 0, right? Because gamma is a primitive element of a true code word polynomial. It goes to 0. This was stated above, right? It was stated right at the beginning. I can't get to back that far. I'm going to lose myself. But gamma, the code word polynomial for this gamma will be 0. And actually, what you can show is for gamma cubed it will also be 0. So the reason for this is something that I haven't shown you, but it's very interesting, is that x in a field, x plus y to the p, it actually equals x to the p plus y to the p. This actually ends up being true for a finite field. And well, we know that x, y to the ij to the p is equal to x I to the p x j y j to the p. And so in general, any polynomial in a finite field, it actually behaves really nicely. Where is this in the notes? This is under the proof for it's under a proof somewhere. It was in the notes last year, I think. Where was this? I'm trying to remember. It's in the notes. It's in the notes. Try and find this. Because I'm doing a disservice by not putting it everywhere. Okay, so this is what we have right now. We have d of gamma is equal to x to gamma I plus gamma j, and d of gamma cubed is equal to gamma to the 3i plus gamma to the 3j. But we also knew that this was equal to gamma to the 4th, and this was equal to gamma to the 8th. So in principle, we're done, right? If we just tested every I and j, we would find one eventually where we would get gamma to the 4th and gamma to the 8th. Yeah? Yeah?
Why are we doing the d gamma cubes, not the d gamma cubes?
Because it's not in the syndrome. We just calculated it. It's in.
But why is that? Very told us that. I think it was 2 gammas.
Why is this the case?
Yeah.
Ask Thomas Ritz. Yeah. I think there's something to do with if there's one error versus 2 errors, the multiplication might get mixed up in the proof. There's something weird happening here. I don't know. I did this course like last year, so I've completely forgotten. But it's Thomas Ritz. We're trying to just do an example here, just to see how things really are working, and you can get into the details if you want. Yeah. Okay, so well, there's actually something that we can do to make our lives better, so we don't have to check all the i's and all the j's. And what we do is we calculate these two terms, si and s3. So what this has done is we've just put more symbols on the board. But what it actually really lets us do is we can calculate, by putting these two things together, we can cube this expression. Right? We can cube that one, and then subtract off S3. And what we will end up is we're trying to isolate the product, and we're trying to isolate the sum. Well, we have two elements. The product of the elements is something, and the sum of the elements is something else. How can we find out what those two things are, the i's and the j's? Well, it turns out something really nice from high school is that we can use Vieta's theorem. What Vieta's theorem is we can construct this polynomial. Remember, for a polynomial, we have that ax squared plus bx plus c. If we have alpha and beta are roots, then we know that alpha times beta is equal to c divided by a, and alpha plus beta is equal to negative b divided by a. Yeah? And so what we have is, well, this looks like this, and this looks like this. Okay. So what we're doing is we're using this formula. And so now we just have to test this polynomial. what are the roots of this polynomial? That will be our gamma I and gamma j. Okay. And so we did test terms. So in general, there are like 15 of these. You're going to test about 7 if we run into one, and then maybe you only have to test 15 though, instead of having to test 15 times 15, right? So this makes our lives a little bit easier. And what you will find, this is a particularly awful case. Gamma to the 10 and gamma to the 12 were where the errors were, because those were the roots of this polynomial. And so we can just corrupt our D and get an invalid code word. Remember, we're trying to decode, which means we want the message, so we have to take off the armor. So this is our message, which is nice. It's a nice message, right? It's just 1 and a bunch of zeros, so somebody's happy with me. Right. And that's the end of BCH coding. Big breath, right? That will make, again, going through Thomas Briggs's problem 86, beautiful. Right? It's a beautiful, I think it's 11 years old at this point, but it's really, you do that and then you really get a feel for the subject, okay? All right. So, next up is cryptography and ciphers. So, how does this work? So, let's say that we have a message, and we want to encrypt the message such that nobody can tell what the message is except me. So let's say, here's a typical diagram. So we have me and we have you, and somebody's in the middle. So I'm trying to send you a message M, and it goes through, and you get a message, let's say, it goes through the open internet, and there's somebody in the middle, and they're a villain, and they're trying to figure out exactly what I'm saying to you. And so we want to try and figure out a way that from sending from me to you, the villain in the middle can't figure out what the message is. No matter how much they know about how I encrypted the message, we want it to be the case that they can't figure out what I said to you. And this is what encryption is all about. So we need an encryption algorithm. We also need a decryption algorithm. These are going to be inverses of each other. And generally, the way that we keep the villain from knowing what we have, what are my messages, is by having a key. And the key is just, maybe it's a key that I give you. And so you can use the key, put it into the decryption algorithm, and it'll tell you, okay, this is how you decrypt my encrypted message. All right, so yes, so ideally, an encryption algorithm should be very hard to decrypt for a villain in the middle. So here's a couple of ciphers. First is the Caesar cipher. Caesar cipher was famously used by Julius Caesar, and what it is you take your alphabet and you shift it by some amount. So here, my key is going to be 3. You can also use the key is equal to D, which means A gets shifted to D. So the key is equal to plus 3, means that I'm going to shift my whole alphabet across by 3. So A goes to D, B goes to E, and so on. See, this should be a... And that's a Caesar cipher. To decrypt the Caesar cipher is pretty easy. All you have to do is add with no 3. That's it. But it's actually also very easy to figure out what's going on. The reason for this is that it doesn't change the letter frequencies. So that means that if there is a lot of E's in your original message, if I shift it by 3, that means your E's are going to go to H's. And so there's going to be a lot of H's in your final message. So I can guess, oh, P is probably equal to 3. And I guess that we're done, right? We've decoded your message, the villain wins. So it's not the best. Here's another cipher. Well, this is called a substitution cipher. And instead of just taking our alphabet and shifting it, we just completely randomize it. So we just completely randomize it. So here's something at the bottom. It's a complete one type of complete randomization. So how many keys are there? Well, how many ways can I encrypt it? Well, there's going to be, I can take A to 26 elements, and then I have 25 elements left. B goes to 1 of 25, C goes to 1 of 26, and so on. So there's going to be 26 factorial keys. Pretty hard to break. But it also means that you have to store a lot of information for a key. So, you know, it's good, but, you know, it's heavy. It's a heavy code. So, anything else that I need to say about this? Ciphertext, 25 ways, and I think we're good. Okay, so, third cipher is a transposition cipher. I'm going to give you a message, and what I'm going to do is I'm going to break my message apart into blocks of length r. What that means is that I'm going to apply a fixed permutation to each of the elements in my block of length r. So maybe my first element in my block will go to the third element, the second will go to the first, the third will go to the fourth will go to the second. So if I were to yell Thomas Fritz, then in the first block, length 4, so remember r is equal to 4 in this case, I will take, okay, first element is t, it's going to become my third element. My second element is h, it's going to become my first element. And I would do that for the length of the block, for the message. Okay. This is what we call a transposition cipher. You can stack a transposition cipher on top of a substitution cipher, so the randomizing cipher on top of this transposition cipher, and it makes it harder to break. That's called a product cipher. Okay? So that's called a product cipher. Here's the final type of cipher I want to talk about, and this is it's a French word, but I'm going to recognize it because I think it sounds cool. It's called the visionary cipher. The visionary cipher, what we do is we again break our message into blocks of length r, so maybe this time r is equal to 3, and then we apply a Caesar cipher to every single element of that block. So I'm going to say my first element of that block, I'm going to shift it down by 1 in the alphabet. The second element, I'm going to shift it down by 2. The third element, I'm going to shift it down by 3. So MAT, HOC, HSO, and C. This goes down to NCWIURD, because I'm shifting my M by 1, my H by 1, and C by 1. I'm shifting my A by 2, my T by 3, and so on. Okay, this is what's called a visionary cipher. And this is hard to break. This is hard to break. But we can break it anyway. And we can break it anyway using this thing called Kaczynski's method. And Kaczynski's method is we're going to find the length of the blocks. And then we're going to guess. But finding the lengths of the blocks makes it a lot easier to guess a key. Because then we just have 26 times 26 times 26, like however many. We only have like r many Caesar ciphers to break. Alright, so how are we going to do it? We're going to start by estimating this thing called the index of coincidence. The index of coincidence is basically, it's if I give you 2 letters in your code, your encoded message, what is the probability that they're the same? For a really long message, the index of coincidence is going to look like this thing called the probability of coincidence. Probability of coincidence is, for the really real English language, spoken in everyday life, if you look at 2 letters, what's the probability that those are the same? That's called the index of coincidence. For a really long message, it's going to start approximating the index of coincidence for our message, 2 letters are the same, is going to start looking like the probability for in the general English language, the 2 letters are the same. And this is really what we're going to do to help us break this code. We can estimate the index of coincidence like this. For a message M of length n, we can look at the frequency, how often each letter shows up, square them, add them together, subtract n squared minus 1. This is a combinatorial argument. I'm sure Thomas Fritz goes through this at some point. It's just combinatorics. Yeah, nothing much to say about this. But this is the index of coincidence. So how do we use this to get the block length? Here's how we do it. Really ugly formula. Really ugly, in fact. The reason for these weird numbers is, again, combinatorics, but it's combinatorics specific to the English language. So somebody has gone out and they figured out the relevant probabilities to put into this formula, and those just show up as numbers. So for the English language, this turns out to be true. You are expected to at least be aware of where these numbers come from. Thomas Britz can do that way better than I can, because combinatorics was not my best subject. But this last number at the end, whoopsies. This last number at the end, this is, oh, not this number, this number here. This is approximately 1 on 26, which means that it's counting the number of letters. The equal likelihood that two letters are the same is about the same as the probability that I pick a random letter. So there are arguments like this that show up to figure out what exactly these numbers are and where they come from. Right, so let's apply Kaczynski's method. An English message is enciphered like this. All right, and we're given a table, frequency table, for even and odd positions. Calculate the index of coincidence. So what we're going to do is we're going to say IC is equal to the sum of the frequencies squared minus n over n squared minus 1 over minus n. Right? And what that's going to look like is I can look at my table. How many times does A show up? Well, in the even positions it shows up twice, in the odd positions it shows up 3 times. That's going to be 5 times. So that's where this 5 comes from. So A shows up 5 times, B shows up twice, Z shows up twice, minus 51 because our message was length 51, divide by 51 squared minus 51, and you'll get this as an estimate for your index of coincidence, how likely it is that if you pick 2 elements that they're going to be the same. Right, and then we can put it into this formula that we had, and we can find the length of our blocks for our visionary cipher. It's 2.8, which means that our block, our visionary cipher, had a code length for a code word into blocks of length 2. Or 3. 2 or 3. R is actually a really good estimate though. So it's only going to be probably plus or minus 1 from where it is. It's going to be either the ceiling or the floor. Turns out it goes really far away quite quickly. So R is a pretty damn good estimate for the block length, okay? Alright, and now the final part was, hey, look at this message. We know that R is equal to 2. Decipher it. And this is hard. Not hard, but it takes a lot of guesswork. There's nothing else that we know. Nothing else from the theory tells us anything about how to decipher this. We just have to do it. How do we do it? Well, what we're going to do is what I would usually do, and in years past is I would say, okay, go to an online calculator and try a bunch of keys. I can't do that this time. So here's a method that you can try, is you could do, we know it's a block length, we know the code word is length 2. So that means there's going to be 2 Caesar ciphers. What I'm going to do is I'm going to write my code word as KMHZ HTSQOWW, and I'm going even letters on the top row and odd letters on the bottom row. Okay? Or no, the other way around. Odd letters on the top row, even letters on the bottom row. And that means I'm breaking apart my code into the 2 Caesar ciphers. Alright, so that's the first step. The second step is to figure out if we can try and figure out any of the words. So, just by looking at the form, this Q here is screaming at me. It's either an A or an I, because there's only 2 English words with an A or an I in it. So you've got to check. Q shows up in the bottom. Now, the shift from Q to A or Q to I, you can calculate. And if you do that, all I can tell you is that you can check for Q is equal to I, and you get I as your second letter in your keyword. Then what you have to do is you have to try and look at the code and try and squint your eyes and see, is there anything else that kind of looks like a word? So these 3-letter words are also really good to look at, because they're probably like and the and something like that. So if one of those you can simplify down to a the, that's really good. So maybe an and. So really, all I can tell you is look at the single letter words, look at the 2-letter words, try and figure out what you can by guess and check. There's nothing more I can tell you. In the past, I would say go to an online calculator, type in all of the possible real English words that are length 2, and eventually you'd get it. Or you know the last one is I, and then you can just guess A, B, C, D, E, F, G by spreading your finger across the keyboard, right? Just by going drr, 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 you figure it out eventually. So yeah, I don't know if he's going to ask this. This was in a paper exam, so it's not impossible. The last thing for the day. Last thing is this thing called public key cryptography. So the keys that I have been talking about are they have an issue, and that is that you have to know the key, and I have to tell you in private. And I wouldn't want to do that. I want to give you the key over the internet, and people can intercept that key, and it's not good. So, how do we get around this? Well, we get around it by having a public key and a private key. So the private key is something that you store on your person, in your brain, in your own servers. And the public key is something that you spread out to the world. Hey, if you want to message me, use this public key. So then people can come in and they can message you, and you can decrypt their messages. All right? And that's the way that public key cryptography works. One of the things that we let our public keys do is we let them, they can be arbitrary, but we usually let them, especially for RSA, in order for a villain to be able to decrypt our message, they would have to solve a hard problem. And this is one of the hard problems. It's called the discrete logarithm problem. We'll see what that is when we go through RSA, which is right now. Okay, so RSA. This is a really cool, really cool. It's really cool. So how does it work? Oh no, I don't have my blank slide. Oh well, it is what it is. So how does RSA work? So let's say I'm over here. Hello. Oh, I don't have that long a hair. And I'm sharing over the internet, and you're you over here. And you want to send me a message. But in the middle, there's a villain. And you can tell he's a villain because he's got a top hat. Right? And he's got evil eyes. Rah. He's going to intercept our message. So how am I going to encrypt my message such that the villain can't intercept? The way I'm going to do it is I'm going to do it following this process. First, I come up with a couple large primes. So P and Q, these are two large primes. So for us, let's say that P is equal to 43 and Q is equal to 47. This is large enough. Okay? Then what I do is I multiply them together. PQ. And this is 2021. If only there was a paper exam in 2021. Alright, so then what you do is you calculate 5n. The reason that you calculate 5n will be shown later, okay? But for now, this is the algorithm. And you do 5n, that's going to be 42 times 46, because these two primes, and phi of a prime number is that prime number minus 1. And that's going to turn out to be 1932. Okay. The next thing that we do is we can choose an encryption key. So my encryption key has to be coprime E and 5n. Their GCD has to be equal to 1. So I'm going to pick E is equal to 5. Okay? Just pick it. I've known pretty well E is equal to 5. The reason I choose E equals 5 is because it's nice and small, and I can see that 1932 is certainly not a multiple of 5. Alright, and now we have to do my least favorite bit of the course, which is find a decryption key. And the decryption key is going to be that element, which is equivalent to 1, 5n. So I take 5d, because my d is equal to 5, and it's equivalent to 1 mod 5n. Alright, so how do I do this? Well, I have to use the extended Euclidean algorithm. So let's just do that. 5d is equivalent to 1. That's the same as 5d is equal to 1 plus some multiple of 5n. But we know 5n, that was 1932. So it's equal to 1 plus 1932j. Alright, so how do we do the extended Euclidean algorithm? What we have to do is we have to say, okay, I'm going to factorize 1932. That turns out to be equal to 5 times something plus 2. And that's something you can use a calculator and you can just get it's 836. 836 times 5. Alright, the next step in our Euclidean algorithm is to write 5 instead of 2. It's 2 times 2 plus 1. And then we want to get rid of these 2's. Because the 2's, they're not going to be the equation that we want, so it's going to substitute them out. How are we going to substitute them out? We're going to multiply this equation by 2. So we're going to have 2 times 1932 is equal to 2 times 386 turns out to be 772 times 5 plus 2 times 2. But we know 2 times 2 is equal to 5 minus 1. So everyone knows that 2 times 2 is equal to 4, but only very few people know that 2 times 2 is also 5 minus 1. So this is going to be 5 minus 1, which means we're going to get 773 times 5 minus 1 is equal to 2 times 1932. And so that means that our value for D is equal to 773. Okay, so that's 773. This is really causing lag now. So D is equal to 1773. Now, to encrypt a message, now you come up with a message you want to send me. It's in your head. Message ends in your head, and you want to encrypt it. The way you're going to do that is I'm going to scream out to you, hey, E and N. And what you're going to do is you're going to take a message, raise it to the power of E, and mod N. Okay? But now the builder knows what E and N are. So what you're going to do is you're just going to take a message to the power of E, mod up. Alright, and then you're going to scream that back to me. You're going to scream it back to me. What I'm going to do is when I get your encrypted message, is I'm going to raise it to the dth power. Alright? So if I raise it to the dth power, what I'm going to end up with is I'm going to get me to the power of d. Now me to the power of d, we're going to get med. I claim that this is equivalent to m. The reason that's equivalent to m is because ed was equivalent to 1 mod phi of n. And that means that ed is equal to some other multiple k of phi of n plus 1. What we know from Euler's theorem, at the very beginning, it was when we looked at Fermat's little theorem, we looked at this, is that m to the phi of n is equivalent to 1. And so, because m to the phi of n is equivalent to 1, I know that m to the k phi of n plus 1 is equivalent to m to the m times 1, which is m. So, that is RSA. I've gone through one example of RSA. So if I were to say encrypt the message m, if you wanted to send me the message 1738, then what you would do is you would take 1738 to the 5th power, because that's what the encryption thing was, that's what I sent you, that was the public key, and you would write that mod 2081. You do that, put that into kcalc, you would get a number. That number turns out to be 234. Now I would get 234. I raise that to the dth power, which is 773 mod 2021, and I would end up with your m is equal to 1738. Alright, that's RSA. Now we're up to the final slide, final concept. We read the sigh of relief after this. It's called the unicity distance. We've got a lot of codes and we've got a lot of keys. How do we know that if I give you a message, that message is uniquely decipherable? right? We liked that in the beginning of the course. Maybe we don't like that here, right? Maybe if somebody's guessing the keys, it could be good if they could guess a message that is wrong, right? So what we're trying to estimate here is the number of elements in a message such that it is uniquely decipherable with one key. Okay. There could be another key that decrypts the message into readable English text, but it's not the key that I actually was using. Okay? So what's the distance? How many letters do I have to give you in a message for it to be uniquely decodable? And that's estimated by this unicity distance. This is the formula. But for English, we can do again combinatorial arguments, and it simplifies down super nicely into the ceiling of log base 2 of the number of keys that were possible divided by 3.2. Here's the proof of that. So for English, we have Q is equal to 26, that's how many letters are in the alphabet, and R is equal to 1.5, that's the information rate, so that's specific to English. So following that, you just get the formula. Okay, and then of course you have H, which is the entropy, which just goes to log base 2. Okay, so let's do one last example at the very end. The product cipher is formed with 26 letters. So remember, product cipher was when we had two ciphers laid on top of each other. It's by the way called code stacking, and it is if one of your codes is decipherable, this becomes bad practice. Anyway, product cipher, you might as well have just used a better cipher, but whatever. You're using a product cipher. It's a substitution cipher and a transposition cipher. So substitution was our randomization cipher, and transposition was when we broke it apart into blocks and then randomized it within those blocks. So transposition length 9 and substitution. So find the number of possible keys. So our substitution cipher, that will give us 26 factorial possible keys. And our transposition cipher, breaking things apart into length 9 and randomizing those, will give us 9 factorial possible keys. So that's how many possible keys there are. The unicity distance, you can plug it into the kcalc. Log base 2 of a big number will become a reasonable number. Divided by 3.2, it'll be even more reasonable. And you get 34. So, how do we use that? We use it like this. A message of length 50 is enciphered using this product cipher, and the resulting cipher text is intercepted by our villain, Eve. And imagine Eve could try all possible keys. It's a lot of computing power, but she's trying all of them. And what would Eve expect to decipher the text in a unique way? Well, we've got 50 elements in the message that we've accidentally transmitted to Eve. And so, because 50 is bigger than the unicity distance, 34, then yes, actually Eve would expect to uniquely decipher our encoded message. So for words though, you actually don't look to maximize the unicity distance, you look to just make your code better and harder to crack. That's generally what it looks like. Right, anything else? Anything else? No, I don't think so. I think that's the end. Wow, that's it. Done. That is the end of information codes and ciphers as a course. It's also, I think, the last time I'm going to be doing a MathSoc revision seminar, which is kind of cute. But I hope you had fun. I hope you had a good time. This is a very good course. So yeah, I think that's it.
Thank you for that wonderful presentation of the app, and everyone joining us on stream or recording. Had a bit of fun with that. And I wish you all best of luck PhD for the win this time. As I say, I think this is a very amazing course, and I feel like that Tom's teaching is it's on Saturday, so try to make the most of it in time for the exam. But I hope you will have fun learning. So this course, so we will end the stream now. And I wish you all best of luck.
Thank you. No worries.
How was that? Feedback. I understood everything. Did everything feel okay?
Yeah.
Any questions?
Oh yeah.
Can you go over anything?
Most of them, I feel that, yeah.
like, do you just say you check it? You know, you get like a 22 numbers. So you just check scores out of the solution.
Yeah. Oh, yeah.
Yeah, just like, yeah, it's
It's most of that is, yeah. This time, when I did the last strike test, no one had definitely, oh, what's my focus? HI.
yeah.
So, I don't know. To me, it seems a little bit weird that you don't get